Hello, my dear students. Welcome to PW English Medium Class 9th and 10th YouTube channel. My name is Ashok Iski. I'm your physics teacher. Spartans batch. And this batch is purely dedicated for class 10th CBSE students. So in this batch, we are going to start with the very first chapter in physics, that is electricity. Okay. So without wasting the time, let's get into the topic. Okay. So in this particular session, we are going to start with, and we know that this is batch name, that is Spartans batch, and it is purely dedicated for class 10th CBSE students. Okay. And in physics, okay, so in physics, very first chapter, that is electricity. Okay. So in this particular chapter, what are the important topics that we are going to cover, and what are the important questions for your board examination? So all this we will be covering in this particular session. Okay. And this session going to be one short lecture. Okay. So everything we are going to cover in one shot. And in this particular session, we are going to cover with the topics charge, potential difference, then electric current and Ohm's law, and then resistance and resistivity, and next one, that is combination of resistors, and the last one, electrical power, Joule's law of heat. Okay. And this chapter, that is electricity, it is a very important topic in class 10th. Okay. So, and this chapter going to repeat in our class 12th as well. So that is the main reason we have to learn our basics properly in this particular session. Okay. So very first topic, that is the charge. Okay. Let's try to understand what is charge. Okay. So here, when we talk about, okay, when we talk about atom, okay, atom. What is this atom? It is the smallest unit of a matter, right? It is the smallest unit of a matter. When we have idea about atom, okay, and if I consider atom and the center of atom, okay, atom and the center of atom, we call it as a nucleus, right? So in nucleus, we know that proton and neutron particle will be present, and in a orbit, okay, in a orbit, the electrons or electron will be revolving. Okay. So let's try to understand by the simulations. Okay. So here we have, structure of atom, and this part, that is the center of atom, right? Center of atom, we call this one as a, nucleus of an atom. In nucleus, you can see, okay, so first it is the proton, and the next it is the neutron, and the next it is the electron. Okay. And in the nucleus, there is a proton and neutron embedded into the nucleus, and electron will be revolving in this orbit. Okay. And in an atom, there are three particles, right? One is a proton, and the next one neutron, the next one electron, right? So these are subatomic particles. Okay. So when we consider atom, here we are going to notice three subatomic particles, right? The first one, a proton, proton, the next one neutron, and the next one electron. Okay. Electron. And this proton and neutron bounded into the nucleus. Okay. Bounded into the nucleus, and the electron will be revolving around the nucleus, right? So these three particles we call as a, subatomic particles. Okay. Subatomic particles. particles. Okay. And in this subatomic particles, you can see, charge on these subatomic particles. Okay. So when we talk about a proton, neutron, and electron, so for the proton, if we consider a charge that is positively charged, and if we consider electron, this is a negatively charged. And when we consider a neutron, okay, when we consider a neutron, it is the chargeless. Chargeless means it is a zero. Chargeless particle. There is no charge on this neutron. So when we ask, question, how many types of charges are present? There are only two types. Okay, one is positively charged, and the one is negatively charged particle. What about this neutron? It is a chargeless particle. Okay, so first we have to know what is this charge. I'm keep on saying charge, right? What is this charge? Charge is the property of a body. Okay, so this is the reason why the two charges attract as well as repel each other. Okay, so that is, there is a exist of force. Maybe it is a force of attraction or force of repulsion based on the nature. Okay, so let's start with our chapter with the first topic, that is a charge. Hopefully you got to know some basic idea about atom and subatomic particles and a charge, right? So when we talk about a charge, and here we have a definition. Electric charge is a property of a body which is responsible for electrical force between them. Okay, so between them. And electrical force, sir, what about this electrical force? No need to worry about it. Okay, so in detail about this electrical force you are going to learn in a class 12th. So here you need to learn the definition and what is the SI unit. Okay, so we got to know what is the definition and what next? SI unit. What is the SI unit? That is SI unit of a charge, that is a coulomb. Okay, so that is a coulomb, and it is represented by a C, capital letter C. Okay, that is a capital letter C. And a very important point, 1 coulomb of a charge contains how many charges, or else how many electrons? Okay, so for that, by the concept of a quantization of a charge, okay, by the concept of quantization of a charge, quantization means quantity. Okay, in a body, okay, if the body contains a 1 coulomb of a charge, that means how many electrons are presented on that body. Okay, so let's check out according to the property of a quantization of a charge. Okay, so quantization means how many charges are present. Okay, so quantization of a charge, this is the one of the property of a charge. Okay, this is the not important, but for your basic information I'm giving this concept, that is quantization of a charge. Okay, quantization of a charge, and according to that, this charge, it is represented by a Q. Okay, maybe it is a small letter q or else a capital letter Q. Maybe it is a small letter q or small letter q or capital letter Q. Okay, here I have written capital letter Q, and it is given by Ne. Actually it is a plus or minus Ne, where N is the number of a charged particle present on that body, and Q means a total charge on the body, and E means it is the charge on a body, or else a charge on electron, charge on a proton. Okay, we will see what is this E value. Okay, and according to the concept we can find out how many number of electrons present in 1 coulomb. Okay, so example, if I consider, if a charge is 1 coulomb, okay, if a charge is 1 coulomb and charge on electron, we will see in the next slide, and the value of a charge, maybe let's consider it as the electron. 1 electron, it is about 1.6 into 10 power minus 19 coulomb. Okay, so where did you get this value? This is the basic information of a proton, electron and a neutron. Okay, so if we talk about the basic information of a proton, What about the mass of the proton? So mass of the proton, it is around 1.67 into 10 power minus 27 kg. And a charge, if we talk about a charge, that is a plus 1e. E means a charge, okay? Plus means on a proton, that means it is 1.6 into 10 power minus 19 coulomb. Similarly, with respect to electron, okay, with respect to electron, mass of electron, it is given by 9.1 into 10 power minus 31 kg. Okay, then, and what is the charge on electron? That is minus 1e, that is a minus 1e, that is 1.6. This is a plus and this is a minus. 1.6 into 10 power minus 19 coulomb. And what about the charge? Here, what about the mass of the neutron? Mass of the neutron is nearly equal to mass of the proton. Okay. And coming to the charge, it is a 0. Chargeless particle. Okay, it is a 0. So from this basic data, we have this value. Okay. Now, after substituting and solving the equation, okay, so you need n value, number of electrons. Okay, so number of electrons, if we consider, see this positive and negative, plus or minus indicates the nature of the body, whether that body is a positively charged or a negatively charged. Okay, now, so here 1 coulomb, that equals to, ignore about this plus and minus sign. Okay, so n value you need to calculate. And what about the E value? That is 1.6 into 10 power minus 19 coulomb. Okay, so rearrange this equation. 1 divided by 1.6 into 10 power minus 19, 1 coulomb, and this is 1 coulomb. I mean, coulomb. So coulomb get cancelled, and after dividing 1 divided by 1.6 into 10 power minus 19, so you will be having 0.625 into 10 power plus 19. After rearranging this, you'll be having a value 6.25 into 10 power 18 electrons. Okay, 18 electrons, n value. Got it? Now, so already we got to know what is the charge. Charge is the property of a body, okay, which is responsible for electrical force between them. Okay, then SI unit, it is the coulomb and represented by capital letter C. And 1 coulomb of a charge contains how many electrons? 6.25 into 10 power 18 electrons. Then let's see what is the next concept. That is the types of a charge. Already we got to know. Okay, there are, if we consider the subatomic particles, that is the, 3 subatomic particles: proton, electron, and neutron. Neutron is, it is the chargeless particle. Then how many types of a charges are there? 2 types. Okay, so basically we have a 2 types of a charge. Okay, the first one, okay, these charges, okay, are divided into 2 types. The first one, okay, if we consider first one, positively charged. The first one, positively charged. Okay, positive or negative, that's all. Okay, positive or negative. So positive charge, and the next one, negative. And example for, okay, example for positive charge, here you can consider proton. You can consider proton. And example for a negative charge, you can consider an electron. Okay, an electron. Got it? Now, charge on 1 electron, already we know that from the basic data. Okay, for that basic data, it is not there in your NCERT textbook or CBSE textbook. Okay, 1.6 into 10 power minus 19 coulomb. So here 1.6 into 10 power minus 19 coulomb, which indicates a magnitude of electrons, and this negative sign indicates it is the negatively charged particle. Electron is a negatively charged particle. Then, as it is for a charge on 1 proton, that is plus 1.6 into 10 power minus 19 coulomb. Okay, so this is data of a charge on 1 electron and charge on 1 proton. Then already we know that 1 coulomb of a charge has 6.25 into 10 power 18 electrons. Okay, 18 electrons. Okay, so why we don't discuss about in terms of a protons? Because electrons will be free to move from one place to another place, whereas the protons are bounded into the nucleus and they cannot change. Okay, so that is the reason the flow of a charges will be always represented in a conductor. I'm talking about a conductor. Okay, so when we consider a conductor, only electrons will be moving, where protons will be bonded into the nucleus. Okay, that's it. So charge and types of charge, it is done. Now next one, properties of a charge. Okay, so here are properties of a charge. There are two important properties of a charge. Okay, so if we consider according to the definition, okay, by the definition of a charge, it is the property of a body which is responsible for electrical force between them. Okay, so here we have two types of charges, that is the positive charge and a negative charge. So example for a positive charge we have considered proton, and example for a negative charge we have considered electron, right? So what if we bring a two positive charge together, or else what if we bring two negative charges together? What if bring positive as well as negative charges together? What will happen? Let's see. Okay, so if I consider, one is a first case. Okay, first case I'll consider. First case, and the next case we will consider this is the second case. This is the second case, and the third case. Third case, and the next. This third case, and here I don't have a space. I'll write it on the top. Yes, here I have considered four cases. Okay, so let me consider this is the first case, and this is the second case, and this is third case, and this is the fourth case. Okay, right. So here I'll name these charges as, this is the positively charged and this is positively charged. Okay, then it is the negatively charged and this is also negatively charged. Okay, and here you can see this is positively charged and this is a negatively charged. Here this is a negatively charged and this is positively charged. Okay, now what will happen if we bring a two like charges? Okay, if we bring two like charges, so this charge particle will exert a force on this charge particle, that is the positive. So when we bring a like charges together, what kind of force we can expect? That is the force of repulsion. Okay, so that is the force of repulsion. This particle trying to move away from this particular position. Why? This charge is exerting a force on this charge, but it is not a force of attraction, but it is a force of repulsion. Therefore, it is trying to move away. At the same time, this charge is also exerting a force on this charge particle, and this is also moving away. Okay, so this kind of a force, we call it as a force of repulsion. This kind of a force, we call it as a force of repulsion. In the same way, this is the, yeah, so this is a force and this is the force. Okay, but here you need to take care, the magnitude of a force, okay, magnitude of a force is same but directions are opposite. Now Second case, here also like charges are there. Therefore, you can expect the same repulsion, that is the force of repulsion, right? So force of repulsion you can expect as nature is same. Okay, and then third case, here a positive and here a negative, opposite in nature. Okay, what is the nature of these two charged particles? That is opposite in nature, positive, negative. So this charge exert a force on this negative charge particle and trying to bring this charge particle towards it. Okay, so towards it. At the same time, this charge particle trying to apply or else exert a force on this charge particle and trying to move this charge particle towards it. So here you can consider this is the force of attraction. In the same way, the fourth case. In the same way, this is the fourth case. So here you can expect this is force is what type of a nature? Attraction. And here repulsion. Here a repulsion. And here again a repulsion. And here again repulsion. And here attraction. Okay. Sir, why two negative charges or two positive charges repel each other? Okay. So all these questions, okay, for all these questions, you'll be getting answer in class 12th. Here you need to just know about, what is the nature between 2 point charges. Okay, these are the point charges, right? So this is the force of attraction, force of repulsion, force of repulsion, force of attraction. By these four cases, we can conclude that like charges repulsive in nature and unlike charges are attractive in nature. Got it? So these are the two properties of a charge. Okay, the first one, here you have, properties of a charge, and the first one here you have, that is opposite charges or like charges attract each other. First, see, opposite charges or like charges. Okay, opposite charge, unlike, this one is unlike. Okay, opposite or unlike, it is not like, it is unlike. Okay, and charges attract each other. You can see the fourth case and the third case. Okay, you can see the fourth case and third case, opposite in nature, unlike charges, opposite in nature, unlike charges, negative, positive, positive, negative, attractive in nature. Okay, and the second one, similar charges or like charges repel each other. What is the nature of the force exist between two charges when they are same? That is a repulsion in the nature. Got it? So this is the basic idea of a definition of a charge, SI unit of a charge, and the types of a charge and the properties of a charge. Okay, now what next? So here we have a charge. Already we know that. What after this? So charges may be in the state of rest or maybe in the motion, right? Maybe in the state of motion. So based on state of the charge, here we have a two different branches of this electricity. Okay, so let's see what are those two different branches of physics, or sorry, electricity. Okay, so electricity divided into or categorized into two parts, very important parts. Okay, the first one, if the charges are at rest, if charges are in motion. Okay, so first of all, what is electricity? Electricity means study of charges, study of charge. Okay, study of a charge. It is the, electricity is the branch of physics which deals with a study of a charge. Okay, now, so based on state of the charge, okay, based on the state of the charge, here we have two categories. Okay, if the charges are at rest, we will be having, okay, we will be having, electrostatic. Static means stationary, electrostatic, or static electricity. Okay, static electricity. Done. So what if the charges are in motion? If the charges are in motion, we have a current electricity. We have current electricity. We have current electricity. Yes, current electricity. Yes, we got to know. So this is not important for class 10th. Ignore this one. We have to concentrate on this motion. When the charges are in motion, we can decide that is the current electricity. If the charges are moving, or charges are changing its position, okay, and if the charges are flowing, so this branch we call it as a current electricity. Current means flow, change, move, right? So for our class 10th, we have this topic, current electricity. Okay, so let's start understanding what exactly current electricity means. Okay, so here we can decide current electricity by taking an example. Okay, by taking an example. Okay, so here let's consider a wire. Okay, so in our household circuit we can see three different colors. Okay, maybe red, green and black. So when you see the wire, it is a insulated, that is the rubber. Okay, so what you see outside, that is the colored one. Okay, maybe it is the red, green or black, that is the insulation. Insulation means insulator. It is the property of a material, okay, which do not conduct electricity. Means you do not get a shock if you even touch that wire when the current is flowing. Okay, but inside that insulation, okay, insulated wire, you will be seeing a metallic wire, that is generally a copper wire. Okay, so if you keep on zoom it, okay, if you keep on zoom it, you will be getting to know that is a just uniform wire for a small stretch. Okay, maybe it is in terms of a centimeter or a millimeter. If you see that, it will be in a straight wire, in the form of a straight wire. Okay, so for that, if you zoom it a wire, if you zoom it a wire, it will be look like this. Okay, it will be looks like this. And you're filling, yes. Okay, so this part you will be calling it as a area of cross section, because you will be using these terms. So that is the reason you have to know what is that cross section area. Okay, area of cross section, area of cross section. So this part you'll be calling it as the area of a cross section, and this is also area of a cross section. And there are two ends. Okay, there are two ends. This is end one. If you consider this is first end, then it is end two. Okay, two ends. Or else if you consider this is end one, this one will be end two. Okay, end two. Got it? So here, if I consider electrons, okay, electrons, it is represented by E. Electrons means a charged particle. So electron, I'll be considering only one electron. Okay, so from one point to another point, means another end, if the charge is moving, okay, if the charge is moving, I'll consider one more electron. This electron is also moving. If I consider one more electron, okay, so here if I consider number of electrons, not only three, number of electrons in a wire, if I consider, these electrons are flowing from, or else the number of electrons are moving from one end to another end. What do you call generally? Current electricity, because these charges are in motion. Get your point? Okay, therefore in simple term, can I say current, nothing but electric current. Okay, electric means charges, current means flow. Okay, electric current. So here you need to know the meaning of the term. Therefore it will be very easy, okay, to define the some definitions. So electric current, electric means a charge, and current means a moving or flowing. Getting my point? Okay, so that means we can call it as a current electricity or else electric current. So by the definition, if you see, the rate of flow of, see from this end, the rate of flow of charges. Rate means it is with respect to time. Wherever you see rate means that is indicates not a price. It is instead of a price, it is, time. So rate of flow of a charges flowing through the conductor, or else it is flowing from through the area of the cross section. We call that as a electric current. Got it? So in an examination, how you need to represent your answer. Okay. So first topic in electricity. So that is electric current. Already we know that. Charge flowing. But in detail, let's define it. The total charge. Here, how many charges I have considered? 3 charges. To understand, I have considered 3 charges. That is the 3 electrons. But in a conductor, there will be number of electrons, number of charges, more number. Okay. So that is the reason I am considering, instead of a number, I'll be considering total charges. Okay. Total charges. Now, so definition wise, we can see the total charge passing through any cross section per second. Per second, with respect to time, we are defining the rate of flow, or else the total flow of a charges is called electric current. So here, let me consider one more example. Okay. So here, number of electrons, let's see. Number of electrons, number of electrons, number of electrons, number of electrons, number of electrons. Okay. And they start moving from one end to another end. So this is the one cross section of a conductor, and these charges will be moving end 2. If it is the end 1, this is end 2. Okay. So here number of electrons are crossing through this cross sectional area, right? This area. Therefore, we can define this as a current, electric current. Okay. Now, so by the definition, this is the, this is how you need to define it. And even more simpler definition. Okay. That is the rate of flow of a charge in a circuit. The rate of flow of a charge in a circuit. This is the simplest definition you can consider. Okay. Now, by the definition, we know that, okay, so that current, electric current means a formula, mathematical formula, I equals to Q divided by T. Okay. Or else, sometime you can consider I equals to small letter q divided by T. So this Q indicates a total charge. Q indicates a total charge. Okay. So total charge. And what about the T? That is the T means it is the time. Okay. Time. In 1 second, how many charged particles are moving, are flowing through the area of a cross section? So for example, let's say 4 electrons passing through this area of cross section in 1 second. So according to that, okay, if 4 charges means 4 charges per second, that means it is the 4. Okay. I don't know what is the unit. Therefore, just I'm using a magnitude. Okay. For example, if 4 charges passing in a 2 seconds, okay, in a 2 seconds, therefore it is the 2, right? So it is depends on time as well as, okay, as well as time dependent. This current is a time dependent. Got it? Now, so what is the SI unit? So ignore this one. Okay. Now, what is the SI unit? SI unit of a current. So here you can write, so that is ampere. So ampere nothing but, so ampere, you can write this one as, small letter ampere, and symbolically this is the capital letter A. Okay, symbolically it is the capital letter A. And this A indicates, okay, for example, A means ampere, right? A means ampere. So if I consider unit, how to define this ampere, sir? If I consider this formula, okay, mathematical formula, let's consider this is the mathematical formula, okay. So according to that, unit of current, I means current, right? I means current. So here, let's represent this current as I, okay. Yes, I. Now, so unit of a current equals to unit of a charge, okay, unit of a charge divided by unit of a time, okay. SI unit of a time, unit of time, okay. Now, So unit of a charge, unit of a current, that equals to, what is the unit of a charge? That is a coulomb, right? So represented by, okay, let me write in words only. Coulomb, okay, coulomb divided by unit of a time, that is the second, right? Symbolically, you can write a C divided by S. So here you can write C per S, means a coulomb per second. Okay, this is the coulomb per second. Okay, right. So this a coulomb per second only. Here we can write this one as, okay, this one as, okay. So I'll write this one as, so ampere, that equals to, okay, ampere A, that equals to coulomb divided by second, right? So this can be written as coulomb per, means division can be represented as a per second, okay, per second, or, okay, or another way of writing this one, okay, coulomb, okay, coulomb second only, but here power 1, okay, power 1. Symbolically, how do you represent? Symbolically, how do you represent? So if I consider 1 ampere, okay, if I consider 1 ampere, what happens to this one? 1 coulomb divided by 1 second, right? So this can be written as 1 coulomb per second, or 1 ampere, that is equals to 1 coulomb per second. So you can express any one of the method, okay? You can follow any one of the method. Both are correct, okay? Now, so for example, say, how do you measure a mass of the body? How do you measure a mass of the body? Using beam balance or physical balance. How do you measure a force acting on the body? By spring balance. How do you measure a time? By clock or by watch, right? So then, how do you measure a current, electric current flowing through the circuit? Okay, how do you measure electric current flowing through the circuit? Then here we have a device or else instrument, that is ammeter. Okay, so that device name is ammeter. You can see here, this is the device by which we can measure electric current flowing through the circuit. Got it? So device name is ammeter. Device name is ammeter. Okay, device name is ammeter. And here also you can see this is A. A indicates it is the ammeter. Okay, also it is the measuring values in terms of a ampere only. Okay, in terms of a ampere only. Got it? Okay, now, so how do you define this 1 ampere? Okay, how do you define 1 ampere? See, 1 ampere is nothing but, okay, it is the, 1 ampere is nothing but a current only, right? 1 ampere nothing but a current, unit of a current. How to define this 1 ampere definition wise? Okay, so 1 ampere, easiest definition, okay, easiest definition, okay, the current is said to be 1 ampere, okay, try to understand. The current is said to be 1 ampere, okay, when 1 coulomb of a charge is flowing per unit time, okay, flowing through the circuit per unit time, or else 1 second, okay, right? So definition wise, we will see it, okay. So 1 ampere is nothing but 1 coulomb per second. 1 coulomb per second, okay. By seeing this, you can define this 1 ampere, okay. So 1 ampere, the current said to be 1 ampere when 1 coulomb of a charge flows across any cross section of a conductor in 1 second. See, 1 second and 1 coulomb. Clear? Okay. Then here we have a very important conversions, okay. 1 milliampere. This can, how to read this one? 1 MA, that is 1 milli ampere, okay, 1 milliampere. How to read this one? 1 milliampere. If you see small letter m, okay, so this one can be written as, in terms of ampere, okay, 1 into 10 power minus 3 ampere, okay, or else directly you can write 10 power minus 3 ampere, okay. Now second one, Second one, 1 microampere. How to read this one? 1 microampere. 1 microampere. Micro means, milli means it is a 10 power minus 3. Micro means it is a 10 power minus 6 ampere. Okay. So this can be written as directly 10 power minus 6 ampere. Okay. Then next one, nano ampere. See, 1 Na, small letter Na. Okay. So this one can be, read it as 1 nano ampere. Okay, 1 nano ampere. So this can be written as 1 into 10 power minus 9. Okay. So this nano means a 10 power minus 9. So this can be written as 10 power minus 9 ampere. Got it? So these are the smallest measurement of a current, or else the current is measured in a very small scale. Okay. So this is 1 milliampere, this is 1 microampere, and this is 1 nanoampere. Milli means it is a 10 power minus 3, and micro means it is a 10 power minus 6, and nano means it is a 10 power minus 9. Okay. Now let's move on to the next concept. So electric circuit. Electric circuit means, so electric means charge. Circuit means it is the path. Simple. Okay. Here you need to understand the heading. Then only you will be understanding in the easiest way. So first one, you see, electric means charge. Okay. And circuit means it is the path. Means path for charges. Okay, path for the charges. Just it is a path, but it should be closed. Why it should be closed? To make it a complete circuit. Okay. So based on this, electric circuit, if here we have two types of a circuit. Okay. One is open circuit, another one is a closed circuit. You'll be having one doubt. Sir, when do we say the circuit is open? And when do we say the circuit is a closed one? So simple, when a circuit is open, that means a switch off. Okay, switch off means there is a breakage of the path. Okay, breakage of the path. So that means the charges cannot flow. Therefore, there is no current. If the circuit is said to be closed, that means the path is a closed and continuous path. Therefore, the charges will be flowing in that path. Whenever there is a flow of a charge, then we can consider there is a electric current in that particular circuit. Okay. So now here you can see examples. Okay. So first let me write a definition of electric circuit that is given by a continuous and a closed path. Simple. Okay. It is the continuous and closed path for electric current. Is called an electric current. Okay. This is electric circuit. Okay. This is circuit. It is not a current. It is a circuit. This is circuit, not current. Yes. So this is circuit. Clear? And types of electric circuit. One is open circuit, another one is a closed circuit. Okay. So here you can see this is the bulb. Okay. So this is the bulb, and this is the switch, and this is the battery, and this is the wire connected. Okay. Between the components. Components means the instrument that are connected in the circuit. Okay. Now, so light bulb, one instrument, switch is one instrument, and this wire is also one instrument, and this battery is the source of electric current. Okay. So what is this cell or a battery do? Maybe in your lower grade, okay, you have studied. Okay. Cell or battery. Okay. So what does it do? It converts. Okay. Converts chemical energy to electrical energy. Okay. Electrical energy. Okay. Got it? Now, so here the battery or cell acts as a source of electrical energy. Okay, source of electrical energy. That means it is converting chemical energy into electrical energy. So what happens is the charge just starts flowing through the wire. So when switch is closed means when a switch is on. Okay, here I'll consider first example. Okay, first case, that is the circuit is open. So circuit is open means here the switch is off state. Switch is off state. When you just look at your room, okay, study room, when you put on a switch, then only your electronic devices starts operating, right? Maybe it is the fan, maybe it is the light. Okay, so when you switch it off, then what happens? Those electronic instruments or electric devices stop operating. Am I right? So in the same way, when switch is off, that means there is a breakage of a path. So here, in the circuit, switch off means how to represent it. This is how you can represent. There is a breakage. So there is a breakage. There is no continuous path. Path is there, but there is no continuous path. Sir, path is there, but there is no continuous path. What does it mean? See, there is a breakage. Means it's kind of a bridge. Okay. So let's consider one example. So between two villages, there is a one river. Okay. There is a one river. To cross that, what you will do? You'll be looking for a bridge. So that bridge, if it is operating, means if it is a closed, or else it is connected between one village to another village. So the people can, commute from one place to another place, or else the people will travel from one village to another village. In the same way, when this path is open, that means there is no bridge. Is it possible for the village people to cross that? In other methods are there, but without a bridge. I'm talking about just in terms of a bridge. If there is only one option, that is the bridge. It is not possible for the village people to cross that river. In the same way, the charges cannot pass through it. So therefore, the current will not flow. When there is no current, the bulb will not glow. So that is the reason here we have indicated with a cross. That means the electric bulb is not operating. Get your point? And the next case, if I consider, if I put a switch on, that means I'm creating a path for this. Okay, I'm creating a path for the electric current. So now here connected, switch on. So in this case, switch on. If a switch is on, there is a connection between these 2 points. That means the connection, that is the bridge connection between two villages. Therefore, village people can move one village to another village. In the same way, the charges will start moving, or else the charges will start flow from one end to other end. So hence the bulb will glow. So this is the second case I have shown in the second case. Okay, I have shown in the second case. So here see, this is the this is open circuit. Okay, when we say this is the open circuit, see there is a plug key. Okay, this is the plug key. If there is no dot, okay, if there is no dot, that means the switch is off. Okay, or else the circuit is open. If a switch is closed, means represent with a dot, that means the bulb is glowing. That means there is a flow of current. In this case, there is no flow of current. Okay, so you can put it as a cross and here write a sign. Okay, so that means directly we can say that there are two types of electric circuit, that is open circuit. Okay, open circuit. In open circuit, what happens to the current? No current. Okay, no flow of current. Okay, no flow of a current. Okay, I'll write. Okay, no flow of I. And closed circuit. Closed circuit. Closed circuit. In this case, there is a flow of a current. There is a flow of current. So this is all about electric current and electric circuit. So there are some different components that we are using in electric circuit. But how to represent that? For example, in household circuit, we use AC, we use a fuse, we use a fan, we use a bulb, we use a TV, and all so many electronic apparatus or else electronic devices. How to represent those, electrical appliances in the circuit. Okay, in easiest way we have to do it, right? So we cannot draw always a fan, we cannot draw always, AC, we cannot draw always a TV. So in simplest way, how to represent all these electronic devices in an electronic circuit. Okay, so let's see the next one. Okay, before that, so here we have a simple question. The question says, that is the numerical question, a current of 0.5 ampere is drawn by a filament of an electric bulb for a 10 minutes. Okay, so here they have given a time also, and current they have given 0.5 ampere. Find the amount of electric charge that flows through the circuit. So here they have asked, that a charge, number of a charge, total number of a charge they are asking. How to calculate it? If you want a full marks in a numericals, okay, especially in a physics, okay, especially in a physics, if you want a full marks in solving a numerical problems, you need to follow some systematic procedure. What is that procedure? So first, what you need to do is data. Write down data. Write down a data. Okay. So after writing data, what is they have given? The first one is current, right? So first one is current they have given, that is 0.5 ampere. The next one, a time they have given. Okay. Time they have given 10 minutes. Okay. So 10 minutes. But we have to, what is the second step? First, writing data. Okay, here sideways I'll write. Okay, first step, writing data. First, writing data. Next one, check units. Check units of the physical quantities. Okay, units of the physical quantities. So here, unit must be in a SI unit. Okay, okay, make it as a SI unit. Now, here 10 minutes, it is not the SI unit of a time. What is the SI unit of a time? That is the second. So, and also we know the conversion, okay? So 1 hour means 60 minutes, right? 60 minutes. And 1 minute means that is 60 seconds, okay? 60 seconds. Therefore, T equals to 10 into, this one can be written as 1 minute. Yes, sir. So 10 into 1, 10 only, and 10 minutes. Okay. So now what I will do, 10 as it is, 1 minute is equals to how many seconds? That is a 60 seconds, right? So now 10 into 6, that is, 60. 10 into 60, that is a 600 second. Okay. Now we got it, a current and then time. Okay. We got it a time as well as a current. Now what they've asked, okay, so they have asked a charge, question mark. So you will be getting for this data, okay, you will be getting, from ranging half mark to 1 mark, okay, depends on the question they have asked for how many marks, okay. So for example, if it is for a 2 marks, you will be getting half mark. If they have asked 3 or more than 3 marks, you will be getting 1 mark for the data, writing data, okay. Then next one, after conversion of units, formula. Formula means what is the relation between this I, T and Q. Okay, what is the relation between I, T and Q? By the definition of a charge, okay, we have a one relation, that is a mathematical relation. So that is given by, okay, so that is given by I is equals to, by the definition of a current, that is I is equals to Q divided by T, right? So we have a current, we have a time, therefore we can find out Q, that is a total charge. So rearrange that equation, cross multiply this, how much you'll get? So Q is equals to I into T. Okay, so this is what we are going to get it. Now, what next? Just you need to substitute. What is the next procedure? Next procedure, put the values in the formula. Put the values. Okay, put the values in the formula. So substitute the values. Q as it is. What about I value? That is 0.5 into 600. Time is 600 seconds. Okay, 600 seconds. I want to eliminate this decimal point. Okay, one decimal point is there. I want to eliminate one decimal point. Therefore, I'll remove 1 0. Therefore, 5 into 60 now. So Q is equals to how much? So 5 into 6, that is a 30 and followed by 1 0. That is the 300 coulomb is the required answer. So this is the answer. Okay, so this is the required answer. Easy. So this is how you need to solve a physics numericals. Okay, now let's move on to the next concept, that is electric potential. Okay, so electric potential, after that electrical circuit diagrams. Okay, right. So here we have electric potential. To understand that is electric potential, first you need to understand rate of flow of a charge. Okay, so flow of a charge, flow of a charge, flow of a charge. Okay, now in a conductor, okay, in a conductor, the charges, that is electrons. Okay, let's consider a conductor, metallic conductor. In metallic conductor, there will be number of free electrons or valence electrons. Okay, do you think those electrons will move by themselves, or they need any external agent to push them from one end to another end? This is our question. Okay, according to the state of a body, here we have a two states. One is state of rest and state of motion. Okay, so from the ninth class, okay, physics, that is the force and laws of motion, where we have learned the first law. Okay, from the first law, Newton's first law, what does it say? If the body is at rest, the body remains in the state of rest. If the body is in motion, the body will remain in the same state, in a same speed and same direction, unless until an external agent acted upon it, right? So that external agent, that is nothing but a force. So if I can consider a conductor, okay, if I consider a conductor, let's consider a conductor. Okay, let's consider a conductor, and I'll consider electrons. Okay, I'll consider electrons. So let's consider one electron for a understanding purpose. Okay, so it is a free electron only. Okay, it is a free to move, but it will not move according to the Newton's first law, because if it is at rest, it will be in the state of rest only. If I apply a force on this, okay, if I apply a force on this, then this particle will start moving and will move towards this, the second end. Means this electrons, okay, these electrons will require external agent to move from one end to another end. What is that external agent? What is that external agent? I'll say that is the potential difference. Directly will not understand. I'll give some examples. Okay, now let's consider isolated system. Isolated system means nothing can enter nor leave the system. Okay, so in this isolated system, here I have a two hot bodies. Okay, here I have two hot bodies. Okay, now they are not in contact. Okay, they are not in contact. So let's say the temperature of this body is 80 degrees Celsius and this body is the 20 degrees Celsius. Okay, now what I will do is I'll bring, or else I'll make them contact. Okay, by bringing together. Okay, bringing these two bodies together. Okay, these two bodies together, 20 degrees Celsius. Now it is the isolated system. Nothing can enter nor leave the system. So what will happen? There is a transfer of heat, right? There is a transfer of heat. But what is the direction? High temperature to low temperature. Hot body to cold body. So here hot body or else high temperature this body is having, and this body is at 20 degrees Celsius. That means a cold body. So heat transfer takes place. Heat transfer takes place. Okay, heat transfer takes place. So until these two bodies, okay, so let's say this will lose its temperature by 5 degrees Celsius and it will gain 25 degrees Celsius, and after some time the temperature will be 70 degrees Celsius and this one will be 30 degrees Celsius, and finally they'll reach equilibrium condition. Equilibrium condition means the same temperature. Same temperature. That is the 50 degree each. Then at this temperature level, no transfer of heat. No transfer of heat. Am I correct? Okay. In the same way, if I consider two tanks, okay, if I consider two tanks, okay, two identical tanks only I'll consider. Two identical tanks I'll consider. Yes. Okay. And it is connected by a small tap. Okay. It is connected by a small tap. Okay. Small tap. Okay. Now, in this particular situation, this is closed one. Okay. Now it is a closed. Okay. It is a closed. Now, the water in the tank, it is completely filled. Okay. And here nothing. Let's say small water is there. Okay. Let's consider small water is there. Small amount of water is there. Okay. Now, what will happen if I open this tap? Okay. Now, let's open. Okay. So let's open. So you can observe these water level, okay, will decrease. Why? The water will flow from this tank to, okay, this tank to this tank. There is a flow of water. And this water tank level keep on increases till these two tanks have a same level. These two tanks have a same level. So this level we call it as a, equilibrium level. Okay, this is equal level, right? Equal level. Even the tap is open. Okay, even if the tap is open, there is no flow of water. Initially there was a flow of water. What is the reason for that? Here till 50 degrees Celsius, there is a transfer of heat. What is the reason for that? Okay. So till 50 degrees Celsius and this equal level, here heat transfer is there. Here water flow is there. Okay. What is the reason? If you check it, here high temperature to the low temperature. Here high level to low level. There is a transfer of heat and transfer of water. But what is the reason? Once it reaches 50 degrees Celsius and once it reaches equal level, there is no transfer of maybe heat or maybe water. When reach equilibrium condition, that is equal. What is the reason? Why there is a transfer of heat? Why there is a transfer of water from one to another? Reason for this case. Okay. Reason difference in temperature. And in this case, difference in water level. Or else you can say hydrostatic pressure. Okay, hydrostatic pressure. So to flow anything, maybe it is the heat, or else for a transfer of some quantity, there must be a difference. Okay, there must be a difference. In this case, there is a difference in temperature. In this case, there is a difference in hydrostatic pressure. At the same time, if the electrons has to move from one end to another end, what should be the difference? That is potential difference. If there is a potential difference, okay, if there is a potential difference, then these electrons will start to move from one end to another end. So hence electric current. Got it? By the definition wise, we'll check it one more time. Okay. And your question, who will provide? Okay, who will provide this a potential difference? Who will provide? That is nothing but by cell or battery. Okay, cell or battery will provide a potential difference. Got it? Now, so first let's try to understand electric potential. Potential means it is the capacity. Okay, simple statement, that is the capacity. Electric, again it is a charge. Again it is a charge. Potential means capacity or ability. Capacity or ability. Okay, now what is the ability? What is the capacity? So here we are relating with the charge, right? Here we are relating with the charge. So to move charge from one place to other place, what we have to do? Okay, for example, I need to move one body from one place to another place. What I have to do? I have to apply a force. Okay, and this body will move. That means there is a force and there is a displacement. Okay, whenever there is a force and a displacement, then we call it as a work done. Okay, when there is a force as well as a displacement, we call it as a work done. Okay, so in the same way, if I consider one conductor, okay, if I consider one conductor, if electrons are moving, okay, rate of flow of electrons from one end to another end, okay, and this indicates a force is acting on the electrons, and these electrons are displacing from here to here, okay, length, along the length. Okay, so there is a displacement of electrons. So displacement nothing but a length along the length. So therefore, can I say force into displacement nothing but a work done? There is a work done on moving these electrons from one end to another end. So that is the capacity. Who will provide this capacity? That is cell or a battery. Simple. Okay, now here we have two terms, potential and potential difference. Potential means it is the reference point is infinite. Okay, reference point is infinite. For example, okay, so let's say this is the infinite point. Okay, this is the infinite point, and this is your reference point, point P. Okay, and here we have a charge Q. We have a charge Q. Okay, I'm applying a force. Okay, I am means in this case there is another charge surrounding it. There is a electric field. Okay, so electric field and force, everything you'll be learning in a class 12. For understanding purpose, I'm considering I am applying a force. Okay, and it will be displacing from infinite position to here. Okay, infinite position to here, point P. Okay, now here there is a work done, right? Work done on a charge, and this one we call it as a electric potential. Okay, from which point to which point? So infinite point to point B. That means final point minus initial point equals to work done to bring a charge. Work done per unit charge. Work done per unit charge on bringing from infinite point to reference point to point P. So this one we call it as a electric potential. But what about electric potential difference? Instead of a reference point infinite, if we consider between known points. Known points means, for example, this is point P, and or else point A. This is point A and point B. Okay, the work done to bring a charge, maybe it is an electron I have considered. Okay, here to bring a positive unit charge from one place to another place, means from point A to point B, then we call it as a potential difference. Got it? So how to define this one? The potential difference between 2 points in an electric circuit. Okay, so let me decide 2 points. So point A and point B. Okay, and charge is at a point B. Okay, let's consider point charge. Okay, this is the charge at a point B. This is the initial position. Okay, and the distance between them. Okay, distance between them, let's say this is a distance or length between the 2 points, and charge is moving towards A. So finally charge is here. Therefore, what I can do, initial position minus final position. What I can write? VA minus VB, that equals to, work done per unit charge. This is the work done. So work done, how do you define? That is the force is applying on this charge and there is a displacement of the charge. So work is done per unit charge. So instead of writing VA minus VB, I'll be writing V. Got it? So finally, mathematically, so V is nothing but work done per unit charge. Work done per unit charge. Okay, clear? So this is the definition you need to write. The first one, it is not required. Okay, ignore that. First one, it is not required. You have to learn the second one. Okay, this is very important. Okay, so this is very important. Okay, this is very important. Clear? Now, what is this I'm writing? Always A and B, or else a conductor, it is nothing but a wire. In physics, instead of calling a wire, we call it as a conductor. It is the metallic body. Okay, so it is the small wire. Okay, thickness is very small, but if you zoom it, it looks like this. Got it? Okay, now next one, yeah, formula already we got it. Electric potential, potential difference. Okay, so electric potential, that is given by work done per unit charge. If you want to calculate work done, you can write a Q into V. Both the formulas are very important. Okay, both the formulas are very important. So definition wise, you can remember this one, and solving numericals, you can remember this one. Okay, now SI unit means, so SI unit of a potential difference. What is the SI unit of a work done? That is the joule. And what is the work SI unit of a charge? That is the coulomb. So here you can write unit of potential difference, that is equals to unit of work done divided by unit of a charge, that is small letter q. Capital letter Q and small letter q indicates a charge only. Okay, now further simplification, unit of this, okay, unit of work done, that is the joule, and represented by capital letter J, divided by unit of a q, that is the coulomb. Okay, so that is C. So finally, if you write it symbolically, that is the J divided by C. So further, you can write, okay, unit of a potential difference, that is the volt. So volt, okay, and it can be written as, okay, joule per coulomb. Already we have discussed how to write units. Okay, so this one, joule per coulomb. So finally you can write this one as, okay, 1 volt, that equals to, if I consider 1 volt, that indicates 1 joule per coulomb. Okay, fine. Now, so device, so like we have discussed, mass is measured by which device? Beam balance or physical balance. And force is measured by a spring balance. Time is measured by watch or clock. In the same way, this electric current is also measured by ammeter. In the same way, how do you measure a potential difference? That is voltmeter. Okay, so that is voltmeter. This one we call it as a voltmeter. Okay, this one we call it as a voltmeter. Yes, voltmeter. Okay, voltmeter. And a device here you can write, that is voltmeter. Got it? And here we have a 1 volt, right? How to define 1 volt? You can see properly. 1 volt. Okay, the potential difference said to be 1 volt. Okay, this is how you need to define. Okay, potential difference said to be 1 volt when 1 joule of work is done on bringing 1 coulomb of a charge from one point to another point. If you know these formulas, these statement, mathematical statement, okay, RMC, you can define this one. Okay, got it? Now, so properly we can see, go through, okay, we can go through this one. So 1 volt is the potential difference between 2 points in a current carrying conductor or else electric circuit when 1 joule of work. So this one, okay, so even if you write this one, you'll get a full marks. Okay, even if you write this one, you'll be getting full marks. When 1 joule of work is done to move a charge of 1 coulomb from one point to another point, this one. one point to another point. That is the point A to point B. Got it? Now, next one. So, here you need to be very careful, okay? In one of the CBS examination, they have asked this question, okay? What is that question? I'll write it in the next slide, okay? Next slide, I'll write it, okay? Potential difference. Potential difference. Potential difference measured by. Potential difference measured by. Second question, potential difference. Okay, so potential difference provided by. Just think about it. Okay, pause the video and think about it. Okay, so here you need to concentrate on these two words, that is the measured by and provided by. Okay, so when we talk about a measured, that means we are talking about a device. Okay, measuring device. So that is voltmeter. Voltmeter. But when you talk about a provide, means who will provide this potential difference? That is cell or battery. Okay, cell or battery or a source. Clear? So these 2 points are very, very important. You can consider it as a note, very important note. Fine. Don't get confused. This is very important point. Clear? Now, let's move on to the question part. NCERT question. That question is, how much work is done moving a charge of a 2 coulomb across 2 points having a potential difference 12 volt? Okay. So first, what you need to do? So first you need to write down the data. Yes, sir. So first we need to write down data. Yes, sir. So what is the data they have given? So let's consider. Let's check out the question. Okay. If possible, read the question twice. Okay. If possible, time permits, read the question properly. Okay. So they have given a charge of a 2 coulomb across 2 points having a potential difference. Okay. Potential difference of a 12 volt. So that means we have a charge, small letter or capital letter Q. Okay. I'll be writing both. Okay. So it is a 2 coulomb. And the next one, potential difference. Potential difference, it is given by V. How much? 12 volt. See, this is the physical quantity potential difference. Okay, here I'll write potential difference. Potential difference V, that is equals to 12 volt. This is a volt, unit of the quantity. Okay, unit of the quantity. Both looks like same, but be careful while writing the unit as well as the physical quantity. Okay, now what you need to do? You need to calculate work done. Now, first, what is the relation between this Q, V and W? By the definition of a potential difference, okay, by the definition of a potential difference, we got to know that is it is the work done per unit charge to bring from one point to another point between the 2 points. Okay, how can I say this is the potential difference, not a potential? By considering these 2 points. Okay, 2 points. Okay, now, so here you need, okay, you need work done. You need to find out a work done. Therefore, Q into V. Q into V. Let's see. Work done formula. After arranging the formula, we got it as a Q dot V or Q into V. Okay. Now, substituting the values. Okay. Substituting the values. W is equals to, what is the Q value? That is the 2. Okay. Into. What is the potential difference? That is the 12. Therefore, work done, that is 24 joule. If you write it just to 24, okay, if you write it just W is equals to 24, okay, if you write this one, you'll lose marks. SI unit is very, very important. That is the W is equals to 24 joule. Got it? So this is the complete presentation of a question along with the answers. Okay, so you'll be getting full marks. No deduction for this kind of, presentation. Now, so here circuit diagrams. So circuit diagrams means the components is expressed by the circuit symbol. Okay, for example, bulb. How can we show in the circuit? If I consider, a cell or battery, how to represent that in the circuit. If I consider a resistor, how to represent that resistor in a circuit. Okay, so here MCQ base, MCQ means multiple choice question. Okay, they can ask these symbols. Okay, so first one you can see the components, the second one symbols. So first one you see, that is electric cell. So when you see electric cell, so here one side it is the length is more, another side it is the length is less. Okay, so two parallel lines only, but the length if we consider the larger length, okay, the larger length indicates positive high potential and the negative sign indicates a low potential. Okay, now second one battery. Please go through the circuit symbol. Next one, switch is open. Switch is open means there is no dot inside the circuit. Okay, inside the circuit there is no dot. If the circuit is closed, okay, that indicates a dotted line. Okay, so this is a switch is closed, means switch on and switch off. This is the switch off and this is switch on. Okay, and here you can see there is a dot. So these lines indicates, okay, these line indicates the wires. When we show this dotted line, no, that means both are connected. Two wires are connected. If we show jump like this, okay, if we show a jump like this, that means there is no connection between the wires. Okay, and the next one, that is the bulb. In the circuit you can show this or else this, both are right. And this is the zigzag path. Okay, this one indicates a resistor. The component name is a resistor and the property of that resistance, we'll see that. Okay, and the same zigzag path if we show one arrow or else like this. Okay, so this indicates a variable resistor or rheostat. Okay, variable resistor or rheostat. This point is very, very important. Okay, so these points are very, very important for your exam point of view. Okay, so first one, these two are very important. And A means the instrument or device is ammeter, and ammeter is the device by which we can measure a current flowing through the circuit. The next one, V indicates that is a voltmeter. It is the device by which we can measure the potential difference across the component. Okay, the last one, a fuse. Okay, this is also very important, fuse, and you have to concentrate more on these three. Okay, 8, 9 and 12. Fine. So these are the circuit diagrams. Okay, circuit diagrams means the components which we express in the electric circuit. How do we express a bulb? How do we express a fuse? How do we express a rheostat? How do we express a resistance? How do we express a cell? How do you express a battery? Like this. Okay, etc. Okay, end of the thinking capacity. Now, next one, Ohm's law. This is very, very important one. Already we know that the current and already we know that potential difference. And scientist name. Okay, scientist name. Okay, George Simon Ohm. Who? George Simon Ohm. So he was trying to establish relationship between current as well as the potential difference. Okay, he want to check, is there any relationship between this current as well as the potential difference or else voltage. This potential difference is also called voltage. Okay, right? So George Simon Ohm. George Simon Ohm. So this scientist trying to establish relationship between, okay, relationship between I and V. And we know that I means the current, V means the potential difference. Okay, and this potential difference, okay, P dot D, potential difference is also called voltage. Okay, both are same. Voltage and potential difference both are same. Okay, and he concluded that whenever there is a potential difference, okay, whenever there is a potential difference across the ends of a conductor, then there is a flow of a current. Okay, the first condition, Whenever there is a potential difference across the ends of a conductor, then there is a flow of a current. First step. Second step, he increased the potential difference across the conductor. Okay. How do you know whether he is increasing or decreasing? By using voltmeter. Okay. So whenever he increase the potential difference across the ends of a conductor, the current flowing through the conductor is also increased. And third step, this George Simon Ohm decreased the potential difference across the ends of a conductor. What happened to the current? It is decreased. He concluded that, okay, he concluded that potential difference is directly proportional to the current. Okay, directly proportional means if a potential difference is increased, what happening to the current? It is also increasing. If a potential difference is decreasing, current is also decreasing. So this one we call it as a directly proportional. This is indicates directly proportional. Directly. Okay, directly proportional. Directly proportional. Got it? Directly proportional. Let's see by the simulation. Okay. So Ohm's law. Right. So here you see V, I and R. Okay. So V, I and R. R. What is this R? Let me explain one more time. Okay. So by mathematics, okay, by mathematics, here I want to eliminate this proportionality constant. I want to eliminate this proportionality constant. What I have to use? Okay, this proportionality I have to remove. I have to consider proportionality constant. I need to remove this proportional, so that I need to consider proportional constant. What is that? So this one is given by V is equals to, okay, R into I, or V equals to I into R. Okay. So you'll be having a question. Sir, what is this R? And we know that V means a potential difference and I means a current. And what about this fellow R? That is a resistance. Yes? Yes, sir. And what is this resistance? Resistance is the property of a body, okay? It is the property of body. Okay? It is the property of a body. What does this property do for this potential difference and current? Okay? If there is a one property means there should be a purpose of that particular character, right? So what will this resistor or resistance of a body do for this current as well as a potential difference? Okay, so we will be seeing it later on. Okay, now first try to understand V is equals to IR. V means the potential difference across the conductor, I means the current flowing through it, and R means it is the resistance of a conductor. How these three parameters are related? Okay, these three parameters are related. Let's check out by the simulation. Okay, so here we have yes. Yes. Let's consider V is equals to IR. Okay, so this is actually we call it as a statement of Ohm's law. Ohm's law, that is a George Simon Ohm, gives a one statement. Okay, so that statement only we call it as a Ohm's law. So what is the statement of that Ohm's law? The potential difference across the ends of a conductor. Where is that across? This is the conductor. Okay, let's consider this is the ends of a conductor, both the side. Okay, two ends of the conductor. When we apply a potential difference across the conductor by a cell, cells we are using. Okay, so cells are in series, so we can call it as a battery. Okay, now so the potential difference provided by the battery and potential difference measured by the voltmeter, we can conclude that the potential difference applied across the ends of a conductor, okay, is directly proportional to the I. If I increase, okay, if I increase the potential difference, concentrate on I as well as the V, ignore about R. You can ask, sir, why should we ignore R? Because we are trying to understand what is the relationship between V and I. Okay, so now let's concentrate on this V as well as the I. Okay, so first I'll increase the V. So try to understand. V is increasing. V is increasing. What is happening to the I? I is also increasing. Okay. If I decrease the potential difference, what is happening to the current? Current is also decreasing. Okay. See, increasing. R remains a constant. Okay. R remains a constant. It is because it is a proportionality constant, right? So I'm keep on increasing. The current is increasing. As potential difference increasing, this current is also increasing. If I decrease the potential difference, current is also decreasing. So this relation gives a one statement that we call it as a Ohm's law. Okay. So directly you can say that, okay, according to the statement, whenever there is a potential difference across the ends of a conductor is directly proportional to the current flowing through it at a constant temperature. This condition is must. If you don't write this constant temperature, you are going to lose a marks. Okay. Now, I hopefully, you understand this concept, Ohm's law. Okay. Directly proportional. Now, let's check out Ohm's law. What is this Ohm's law? Okay. So what is this Ohm's law? So this is very, very important. Okay. Very, very important. Very, very important question. Okay. Statement, definitely they'll ask for your board exam. Okay. So statement, what is that statement? We have seen the potential difference V across the ends of a given conductor is directly proportional, not inversely proportional. Inversely proportional means if one quantity increases, other quantity decreases. If one quantity decreases, other quantity increases. Inversely proportional. Inversely proportional. Okay. So like this. If it is decreasing, this one increases. If this is decreasing, this one increases. Inversely proportional. Directly proportional means, for example, same level. If this quantity is increasing, this is also going to increase. If this quantity decreases, this quantity is also going to decrease. So this we call it as a directly proportional and inversely proportional. And in this particular law, that is the Ohm's law, V as well as the I are directly proportional. The proportional to the current flowing. But here, this one is very, very important. Constant temperature. Okay. Why constant temperature? Because as the temperature changes, resistance of the conductor is also going to change. I'll tell you the reason. Okay. Factors affecting the resistance of a conductor. We know that it is the property of a body or else a property of a conductor, but it is also depends on some parameters, right? So in that particular topic, we are going to discuss how the resistance of a conductor changes or else depends. Okay. So based on, experimental verification, we conclude that at a constant temperature means the resistance of a conductor is also constant. The resistance do not change when the temperature is constant. So as per that condition, V is directly proportional to I. You'll be having one question. Sir, what if the temperature is changing? This Ohm's law is still valid? No. For a variable temperature or else variable resistance, this Ohm's law is not valid. Okay, Ohm's law is not valid. Okay, now, so according to that, we got to know the statement. Okay, V is directly proportional to the I. Okay, so that means here V and this is I. Okay, so this is volt. This is the potential difference in volt, and this is the current in a ampere, milliampere, microampere, or nano ampere also. Depends on our scaling. Okay, so as it is directly proportional, if the potential difference is zero, if the potential difference is zero, what happens to the current? That is also zero, because this current depends on a potential difference. If there is no potential difference, there is no flow of a current in the circuit. So that means it is the directly proportional. Therefore, as it is directly proportional, we can consider this is the straight line starting from the origin. Okay, right? So this one gives you a resistance. Okay, the slope means, for example, if I consider this part. Okay, let me consider any point between any 2 points. Okay, between any 2 points. So if I consider this one, this slope means y-axis, change in y-axis. Okay, change in y-axis, this one, and a change in x-axis, right? So this is slope. Slope means change in y-axis and a change in x-axis. Okay, slope means change in y-axis divided by change in x-axis. So according to that, okay, change in y-axis means change in potential difference. That is the delta V divided by along x-axis means delta I. So that means this slope is nothing but resistance. Slope is nothing but resistance because the proportionality constant, that is the R, right? So V is directly proportional to I. Therefore, V after proportional removing, okay, after proportionality, you know, after eliminating proportionality, we can write I into R. So this one we will be getting by the slope. Okay. So finally, R is equals to change in potential difference divided by current. Okay. Right. So by this. So what is this data? See, 0 means 0. Okay. So when voltage is 0, current is also 0. Let's say this is R is equals to V divided by R, right? Sorry, R is equals to V divided by I. So V is 0, I is also 0. Therefore, resistance is 0. Okay. It is starting from 0. If potential difference is 2 and current is 0.5. According to that, okay, so 2 divided by 0.5. So this is going to be 4. Okay, 4. I don't know what is the SI unit. We will see that. Okay. And next one. So potential difference 4 and current is 1. Therefore, it is the 4 only. Okay. 4. Right. So 1 by 2. Yes, 4. So now here it is not exactly, 4. So 6 divided by 1.5. That is the 3 by 2. 3 by 2 means 6 divided by 1.5. Okay. So 1.5. This can be written as 3, 2, and it is also 4. Okay. So 4, 4, it should be, it keep on increasing. Okay. So 4, 4. So these data, okay, we cannot consider. So randomly I'll write now. Okay. So if it is a 2, then it is a 4. And this should be 0. Say it is a 3. 3 means 8. And next one, 4, 5, 3 means it is 3, 11, 1.1. And here 1.1 plus 3, that is the 1.4. Okay. So according to that, you can manage. So you'll be getting R value. Okay. So try to solve these questions. Okay. So here I'll write one more time. Avoid the confusion. Okay. So this is a 0.8 and this is 1.1. This is 1.4. Okay. So try to solve this one. You'll be getting the same kind of a graph. Okay. Now, so here R is there, right? R. What is that R? It is the resistance of a conductor. What is that resistance? Already I told you that is the property of a conductor, current carrying conductor. So what does it do? Opposes flow of current. Okay. Opposes a flow of current. Opposes a flow of current means it is always against a current. If the current is increasing, it will say no, you cannot increase. Okay, so that's what this a property of a body doing, that we call it as a resistance. So resistance is a simple, okay, that is nothing but opposition offered for the flow of a current. Okay, it is like an enemy for the current. It is like an enemy for the current. Okay, now according to the statement of Ohm's law, it states that V is equals to I into R. Now, in terms of R, resistance, in terms of a R, that is the resistance, you can write it as a V divided by I. And here you can see R and I are inversely proportional. Inversely proportional. What does it mean? If, okay, if R increases, what happens to the I? Decreases. If R decreases, current increases. Okay, so it is the inversely, okay, here I have written a directly proportional. It should be inversely proportional. Okay, R is inversely proportional. Inversely proportional. Okay, so if the resistance of a conductor is more, current will be less. If current resistance of a conductor is less, current will be more. Okay, inversely proportional. And what is the SI unit of a resistance of a conductor? Unit of a potential difference, that is the volt, and unit of a current, that is the ampere. So unit of resistance is given by ohm. Okay, in words I'll write it is a ohm, 1 ohm, 1 ohm, that equals to 1 volt divided by 1 ampere. So that can be written as, okay, volt. This one can be written as ampere. Array. This is 1 volt. 1 volt divided by 1 ampere. Okay. So in short, 1 volt divided by 1 ampere. So finally, you can write 1 volt per ampere. So finally, you can write 1 ohm, that is equals to 1 volt per ampere. Okay. Now, how to define this 1 ohm? Resistance of a conductor said to be 1 ohm. Okay. 1 ohm, nothing but it is the SI unit of a resistance, right? So 1 ohm, how to define simply? Okay, in a simplest way, the resistance of a conductor said to be 1 ohm when there is a potential difference of 1 volt, the 1 ampere of a current flowing through it. Or else you can reverse these terms. Okay, how? So 1 ohm, that is the resistance of a conductor said to be 1 ohm if there is a flow of 1 ampere of a current when potential difference is 1 volt. Simple. Okay, so here you can see 1 ohm. 1 ohm. The resistance of a conductor is said to be 1 ohm if a current of 1 ampere flows through it when the potential difference across its end is 1 volt. Easiest way, right? Now, let's move on to the next one. That is the factors affecting resistance. Okay, so factors affecting resistance. For that, first I'll show you the simulations. Okay, so Ohm's law, it is done. Okay, atom structure of atom is also done. Yes, resistance. So here you can see R equals to L divided by A and rho. Okay, so first I'll write this one. Okay, now, so first statement you see the factors affecting resistance of a conductor. If I consider this is the conductor, okay, this is the conductor, and this is one area of a cross section, and this is another side area of a cross section. Okay, now, so this is the A part, that is area of cross section, and this is L. This is L. Okay, and material. Okay, first I'll explain this one. Okay, the factors affecting resistance of a conductor, the resistance of the conductor depends on, okay, depends on R directly proportional to the length. Okay, directly proportional to the length, and inversely proportional to the area of cross section. Why? I'll give simple example. Okay, if I consider a small conductor, means lengthwise. Okay, if I consider small length. Okay, so number of free electrons. Okay, let me consider classroom only. Consider two cases. Okay, one small classroom and another one is big classroom. In which classroom the number of students can occupy more number of seats? Okay, in one classroom and other classroom, comparatively one is bigger, another one is smaller. Obviously, the larger room will occupy more number of students. In the same way, here a conductor, if length is more, the number of free electrons will be more. If length is less, number of free electrons will be less. So what happens when you provide a potential difference? Number of electrons, that is the free electrons, starts colliding. When they collide, the speed of electrons in a conductor reduces. If the flow of charges reduces, means the flow of a current will also reduce. If a current is reducing, what happens to the resistance? Resistance is increasing. So that means more the length, more is the resistance of a conductor. Okay, so first point, it is clear. Okay, first point, it is clear. Second one, area of a cross section is inversely proportional to the resistance. Okay, again consider, say, two identical classroom. Okay, two identical classroom means in one classroom number of students 40, in another classroom number of students are 40. So at the same time, okay, at the same time means during the bell. Okay, so the condition is one classroom door, exit door, is way bigger compared to the another one. Okay, first one or another one. Okay, so one room, classroom, exit door is way bigger than other. So at the same time, nothing but during the bell, okay, all the students start, move out. Okay, so in which classroom, okay, in which classroom it is easier to move out? Definitely that is the classroom which is having, bigger door. Therefore, at the same time, number of students can exit easily compared to the other one. So if the number of students is nothing but a number of electrons, if I consider, okay, at the same time, number of electrons exiting in a bigger door, okay, so that means number of electrons is directly proportional to the rate of flow of charges. Rate of flow of charges is more, means that means the current is more. If the current is more, the resistance of a conductor is less, because it is the inversely proportional, right? So this is also understood. Next one. So length is directly proportional, okay, so length R is directly proportional. The next one, area of a cross section is inversely proportional, okay. So what I will do, I'll combine the both length as well as area of cross section, okay. I want to eliminate this proportional, so that I have to consider proportionality constant. What is that proportionality constant? Equals to rho L divided by A. This is the formula, resistance formula, okay. So that means it depends on the length and area of a cross section and the nature of the material. So this proportionality constant indicates the nature of the material, okay. So this is rho. So rho means it is the nature of the material. Nature of the material. Nature of the material. Nature of the material. What does it indicate? That is indicates number of free electrons. Number of free electrons. Or, okay, number of free electrons. Or what type of material? Okay, nature indicates what type of a material. What type of material? What type of a material? Okay. So example, whether the conductor is made up of a copper or silver or iron. Okay. So this is what, rho indicates nature of the material. Okay, got it. And this nature of the material depends, okay, depends only on number of electrons, that is the valence electrons or free electrons, and it does not depends on any other things, okay. And this one we call it as a, generally we call it as a resistivity of the material, okay, resistivity of a conductor, rho, okay. So here we got to know nature of the material, okay, R is directly proportional to the rho, okay. Now, so this nature of the material indicates, that is nothing but resistivity, not resistance. Resistivity indicates the nature of the material. And another name for this resistivity of a material or resistivity of a conductor, we have another name, specific resistance. Okay, specific resistance. Specific resistance. Got it? Okay, so this is also rho and this is also rho. Fine. Now, next one, and simulation wise we'll see. So according to the formula, R is equals to rho L divided by A. Now, I'll keep this rho as it is. Means nature of the conductor. Means let's consider this is a copper wire, okay. So I'm keeping this a rho, that is the nature of the material, that is nothing but what type of a material, that is a conductor, that is a copper wire I have considered. It is a fixed. Now what I'll do, I'll increase the length, okay. I'll increase the length. Let's see what happens to the resistance of a conductor. So I'm keeping resistivity, means copper. Example, I'm considering copper. Now I'm increasing the length and keeping area is also same. You see, resistance is increasing. You see the length of the conductor decreasing. Now decreasing, what is happening to the resistance? Length of the conductor is decreasing, resistance is also decreasing. If I increase resistance, length of the conductor, if I increase the length of the conductor, what is happening to the resistance? It is also increasing, right? Okay. So that means R is directly proportional to the length of the conductor. Why? Let's consider number of free electrons. These dotted, these dots indicates a number of free electrons. When the length is more, number of free electrons are more. Okay. If length is less, you count the number of dotted dots or number of free electrons, that is also decreasing, right? So hence resistance decreases. Okay. Now I'll keep length is also constant. Now, what if I increase area of cross section? Area of a cross section is nothing but a thickness. Okay, I'll write that also. Area of a cross section is nothing but thickness of the conductor. Thickness of a conductor or else wire. Thickness of the wire. Okay, now, so first I'll increase the area of a cross section, means the thickness I'll increase. Concentrate on this and this. Okay, now increase the thickness. What is happening to the resistance? That is the decreasing. And if I decrease the thickness, that is the area of cross section is decreasing. What is happening to the resistance? It is increasing. You see, if I decrease the area of a cross section, if I increase the area of cross section, nothing but if I increase the thickness, what is happening to the resistance? It is decreasing. Inversely proportional, right? So inversely proportional. If thickness is increased, resistance in what happens? Resistance will decrease. Okay. If a thickness reduces, means thickness reducing means resistance is increasing. Inversely proportional. Got it? Okay. Right. Now, so resistance formula is also done. Next one. Before this conductor and insulators, I have one more concept, that is, yes, specific resistance. Specific resistance means, I told you, that is the nature of the material. Okay, nature of the material. So how to define this one? Okay, by the general formula, R is equals to rho L divided by A. I need this resistivity, specific resistance. Okay, resistivity or specific resistance. Now, if I rearrange this equation, cross multiply this one, R into A divided by L. Okay, now, what if I substitute? Okay, if I substitute, R is equals to A is equals to area of a cross section, nothing but a thickness, 1 meter square, and length is 1 meter. What happens to the resistivity or specific resistance? R is equals to rho is equals to R, in place of A 1, in place of L, that is also 1. So that indicates rho equals to R. That means specific resistance is nothing but resistance of a conductor when area of a cross section is 1 meter square and length is 1 meter. Okay, you see, specific resistance of a conductor is equal to resistance of a conductor of unit length. Unit means that is the 1. Unit area, that is also 1. 1 meter square, 1 meter. Okay, and it depends only on nature of the material. And this point is very important. I'll make it in, I'll mark it with a different color. Therefore, you can concentrate more. And independent of a dimensions. Dimensions means maybe length, maybe width, maybe area of a cross section, area of a cross section, or else volume. So what exactly mean? See, it does not depends on size of the conductor, or else length of the conductor, or else thickness of the conductor, or else volume of the conductor. Ultimately, what type of material it is. So that indicates a resistivity or specific resistance. And this specific resistance or resistivity is different for a different material. Okay, so for copper and for iron, for aluminium, everything is different from each other. Got it? Okay, now, then what is the SI unit of a specific resistance? Okay, let's consider this one. Okay, let's consider this one. here I'll write, after rearranging this one, okay, where to write? I'll write here. So resistivity, that is equals to Ra divided by L for unit, okay, for unit of resistivity. So what is the unit of resistance? That is a ohm. And unit of area, that is a meter square. Unit of a length, that is a meter. And here meter get cancelled. So unit of resistivity, that is the ohm meter. Okay. And this ohm meter, okay, this is ohm meter, unit of resistivity, ohm meter, symbolically ohm meter. Okay. Now here I can write this one as ohm meter. So words I'll write, then I'll write in symbolically, okay, in terms of symbolically. So ohm meter, symbolically ohm meter. Got it? Now, resistivity or resistance is a characteristic property of a material, okay? Already we have discussed, okay? Right. Next one. So based on this resistivity, we have categorized material into three ways, okay? One is conductor, second one insulators, and third one semiconductors, okay? Now let's concentrate only on our conductors, okay? So we will discuss or we can discuss overview of those topics also, okay? But in detail you are going to learn in higher studies, okay? So based on resistivity or based on conductivity of electricity, we have divided our materials into three categories: conductor, insulators, and semiconductors. So first consider our conductors, okay, based on resistivity or conductivity. First one, conductors. First one, it is the conductors. What is that conductors? Conductor means what? So here, the materials which conducts electric current, then we can call it as the conductors. What if the materials do not conduct electricity or else electric current? For example, if I consider iron, it will conduct electricity or else current electricity or electric current. If I consider aluminum, if I consider copper, if I consider any metal, it will conduct current or electric current. Then you can call it as a conductors. All the metals are conductors only. Okay. Now, if I consider a rubber, okay, rubber or else paper or else wood, these materials do not conduct any electric current. Then you can call it as a insulators. And the range between conductors and insulators, we call it as a semiconductors. Okay. So let's see one by one. So first one, conductors, already we got to know. Metals. Okay. So metals. So metals are good conductors due to their low resistivity. Okay. Then alloys used to make heating elements in a toaster, electric iron, and the resistance vary very little with the temperature. Vary means change. There is a small change. Very small change. Okay. So therefore, alloys are used. Alloys means it is a mixture of two or more metals. Okay. It is the mixture. So here we can use heating elements. Okay. Example, toaster or else geyser or else water heater. Okay. Next one, electric iron. Electric iron also, it is the alloy. Okay. All these examples for alloys. And tungsten, it is used in a bulb. Okay. Used in a bulb. Okay. Now, next one, this tungsten used in a bulb as a filament because of high resistivity. Next one, electric fuse. Electric fuse is a safety device. Safety device means whenever there is a large amount of current, this fuse will stop that current by breaking a fuse, means element in it. And this fuse is made up of a lead and tin, of lead and tin. Okay. And the next one, to prevent overloading due to low melting point. Okay. Now, note the resistivity of a conductors and alloys is very low of order. Okay. Here you will be having one question, sir. Do we need to remember? No, not required. Okay. Now, let's move on to the next type, that is the insulators. Already I have discussed. The materials do not conduct current or electric current. Those materials are called insulators. Example, rubbers, wood, paper. Okay. Right. The materials which do not conduct electric current, they possess large value. Why they don't conduct electric current? Means they have, okay, highest resistivity. Okay, highest resistivity compared to metals. The resistivity of insulator is very high. Order, no, order, you know, that is 10 power 12 to 10 power 17. I'll remove that. Okay, it is not visible. 10 power 12 to 10 power 17. Example, okay, example, glass, porcelain, wood, rubber, and plastic. And this porcelain, you may have seen a fuse, okay, company fuse. So white color one, okay, white color one, we call it as a, you know, porcelain. Now, last one, it is the semiconductor. It is semiconductor. And the materials conductivity, okay, materials conductivity lies between conductors and insulators. Those materials are called, you know, semiconductors. Okay. Now, the resistivity of a semiconductors are 10 power 15 to 10 power 16 times less than insulators. Okay, less than insulators. Then example, you can see silicon and germanium. Silicon and germanium. Okay, silicon and germanium. Example for semiconductors, important. Okay, important, silicon and germanium. Now, here question. How much current will an electric bulb draw from 220 volt source if the resistance of a bulb filament is 1200 ohm? First question. And the second question, B. How much current will an electric heater coil draw from 220 volt source if the resistance of a heater coil is 100 ohm? Okay. So here first data. So first part A, data, will note down. Okay. So first data. What is the data? What is the data we have? The first one, how much current will an electric bulb draw? That means I, we need to calculate. And voltage they have given, that is the potential difference, that is 220 volt. And if the resistance of the bulb filament is, resistance they have given 1200 ohm. Okay. Yes. So relation between these three, already we know that from Ohm's law, V is equals to I into R. So here I is equals to V divided by R. So V is 220 divided by R, that is a 1, 2, 2 zeros. Okay. And 1 0 1 0 get cancelled. Okay. 1 0 1 0 get cancelled. And here we have, that is 22 divided by 120. Okay. 120. 120. That is 22 divided by 120. How much? No. It is wrong. Multiplication is happened. 22 divided by 120. Yes. This is after rounding off. Okay. After rounding off, I equals to 0.184 ampere. Okay. So this is the final answer. And the next part, that is the part B. Next part, that is the part B. Data. So data, let's check out the data. Let's check out the data. And data, here you can notice the first one. Okay. How much current? Again, here you need to find out current. Will electric heater coil draw from a 220 volt? That means we have a potential difference of 220 volt and resistance of a coil. How much it is? 100 ohm. 100 ohm. Again from the Ohm's law. Here we have V is equals to I into R. After rearranging this formula, we have V divided by R. After substituting the values, that is 220 divided by resistance, that is 100. Okay, and here you can see 1010 get cancel, and 22 divided by 10. So finally you have answer 2.2 ampere. This is the required solution. Okay, this is the required solution of this question. Fine. Now let's move on to the next again question. Again we have a question. The question says the potential difference between the terminals of an electric heater is 60 volt when it draws a current of 4 ampere from the source. What current will the heater draw if the potential difference is increased to 120 volt? So approaching question is very important. Okay, approaching the question is very important. So first case, they have given potential difference between the terminals of an electric heater is 60 volt when it draws the current of 4 ampere from the source. Okay, when potential difference is 60 volt, the current drawn is how much? 4 ampere. What if the potential difference changes? What happens to the current? The potential difference changes, then current is also going to change. That is our rule, means by the Ohm's law. Now, what current will be, okay, what current will the heater draw if the potential difference is increased to 120 volt? What happens to the current? Current is also increases. Okay, according to the condition, 60 volt 4 ampere means 120 volt. Doubled means that is also should be doubled. Okay, by calculation we have to prove it. And resistance of the conductor they have not given. Okay, so first find out the resistance. Okay, data, first data we have to write. Given data, and here, so first potential difference they have given 60 volt and current drawn, that is a 4 ampere, and resistance of the conductor we don't have. Therefore first we need to find out resistance of the conductor. Therefore by the Ohm's law, V is equals to I into R. As we required R, rearrange that formula, V divided by I. So what is V? That is the 60 divided by 4. Okay, so 60 divided by 4, how much? 60 divided by 4, that is the 15 ohm. Okay, now here I'll be writing R is equals to 15 ohm. This is 15 ohm. Okay, now so resistance value we got to know. Now the potential difference is increased to 120 volt. Then what happens to the current? According to the Ohm's law, as potential difference increases, current in the conductor also increases. So by the Ohm's law, V is equals to I into R, right? And here I need I value. I is equals to V divided by R. What is V? That is a 120 divided by R value, that is a 15. So 15 from here. Okay, so 120 divided by 15. 120 divided by 15. How much it is? 8. So finally you have current value as 8 ampere. If you think logically, okay, you can answer this question within 5 seconds. Okay, how? When 60 volt potential difference, the current is 4 ampere. If the potential difference is doubled, that is the 120, what happens to the current? That is also going to be doubled. That is a 4, double of 4, that is a 8. Okay, double of 4, that is a 8. Okay, now let's move on to the next question again. Question: the resistance of a metal wire of a length 1 meter is 26 ohm. Resistance of a metal wire of a length 1 meter is 26 ohm at 20 degrees Celsius. If the diameter of the wire is 0.3 millimeter, what will be the resistivity of a metal at that temperature? Okay, resistivity, I think it is a resistance. Okay, this is a resistance. Okay. Let's see. We'll calculate resistivity also, no problem. At the temperature, predict the material. Okay, table we do not have. Okay, Using table, we don't have. Okay, fine. Now, so according to the question, first write down the data. Write down the data. So by the data, we can write that is the length of the conductor 1 meter and resistance of the conductor 26 ohm and diameter D that is 0.3 millimeter. Okay. To calculate resistivity, what is the relation between resistance and resistivity? We know that R is equals to rho L divided by A. But we don't have A, that is the area of cross section. Area of cross section, if you see, if we consider a conductor, okay, if we consider a conductor, okay, so this is the area of a conductor. So it looks like a circle only, right? So you can consider it as a pi r square. Okay. So diameter they have given, or radius you can convert. Okay. So radius is half of the diameter, that is 0.3 divided by 2 millimeter, right? So r can be written as 0.3 by 2 into 10 power minus 3 meter. Milli means already we got to know, that is 10 power minus 3. Okay, 10 power minus 3. So here we need resistivity, therefore R into A divided by L after rearranging the formula. Now what we have to do, just we need to substitute the values. Resistance 26. Okay, so first we'll reduce the equation. Directly we don't have values, right? R into pi r square divided by L. Okay, now we have to substitute the values. So this is 26, pi value, that is the 3.14. Okay, pi value, it is the 3.14. Here I'll write pi value 3.14. It is a constant into this one, radius 0.3 divided by 2 into 10 power minus 3 whole square divided by length. It is a 1 meter. Yes, 1 meter. Okay. So now calculations. Okay. So resistivity, that equals to, so let's calculate, that is 0.3 divided by 2, okay, into 0.15, okay, into 3.14, array 0.3 divided by 2 into 0.15, okay, into then 3.14 into 26. Okay, so this is the value of resistivity, that is 1.8369 into, here we have a 10 power minus 3 power 2, that means 10 power minus 6. Okay, ohm meter. So this is the final answer. This is the final answer. So answer. Okay, right. So let's move on to the next concept. Again, one more question. You can expect one question from these exercises. Okay, these questions. A wire of a given material having a length L and area of a cross section A has a resistance of 4 ohm. What would be the resistance of another wire of the same material having a length L by 2 and area of a cross section 2A? Okay. So first let me write down the data because it is very, very important. Okay. So first case, okay. So first case, if you see, so resistance how much? Resistance 4 ohm. Okay. And resistance is also given by rho L divided by A, that equals to 4 ohm. Okay. So let me consider this is the equation. Let me consider this is equation 1. Okay. Equation 1. So next what they are saying, what would be the resistance of another wire of the same material? Means resistivity same. Okay. Same material means material same. Okay. Same material. Same material means resistivity will be same. Okay, same. And new length will be new length. Okay, new length L dash, that is equals to L divided by 2. And area of a cross section, new area of a cross section, that is the 2 times of A. Okay, now new resistance will be, that's what they are asking. What would be the resistance of another wire? Okay, so new resistance will be, here I am writing this one. So rho dash L dash divided by A dash, right? Yes, new. R dash indicates a new resistance. Okay, or else, resistance of another wire. Okay, resistance of another wire. So R dash, that is equals to, as same material, this one going to be the same. And L dash, what is the value? L by 2. And A dash, that is the 2A. Rearrange this one. Rho L divided by 2A into 2. Okay, so R dash, 2 into 2, 4. I'll write it 1 by 4. Bracket of remaining rho L divided by A. Okay, have you seen this one? Rho L divided by A? Yes, from 1. Okay, so from 1. So R dash, that is equals to 1 by 4 into, what is the value of this? 4 ohm. Okay, so 4 get cancelled, and finally you have R dash, that is the resistance of another wire, that is the 1 ohm. Okay, so simple. Approaching question is very, very important. What they have given and what we need to find out. Okay, now let's move on to the next concept, that is combination of resistors in a series. Okay, this is very important. This is very, very important. Okay, so system of resistors. If I consider a system of resistors, okay, so first you need to know what is the difference between resistor and resistance. Resistor, okay, resistor, component, electronic component. Okay, electronic component. Okay, and resistance, property of this one. Okay, property of this component, and resistivity, it is the nature of this electronic component. Okay, so resistor and resistance. If I consider resistors, how does it look like? Okay, so let's have a look. So it is done. Okay, remove this one. So here you can see this one. Okay, this one we call it as a resistor, and property of this resistor we call it as a resistance, or else you can consider conductor. For example, wire, if you consider, okay, if you consider a wire, the property of a conductor is called resistance, which opposes a flow of a current. Okay, the resistance is the property of a conductor which opposes the flow of a current through it. Okay, and resistor, it is the component, electronic component. Don't get confused. Okay, now next one. Resistors in series. So first you need to understand what is the series. Okay, first question, sir, what is series? If the resistor, okay, resistor, it is symbolically, it is given by like this. Okay, so first I'll make a clear cut information for you. Okay, so first let's consider a series. What is this series combination? Okay, if for resistors, number of resistors, okay, number of resistors, this is one resistor and one more resistor is connected immediately at another end. Okay, and the next resistor here. You see, this is resistor 3 and this is resistor 2 and this is resistor 1. So all three resistors are connected one after one, okay, not one by one after one. Means this is the one terminal and this is the second terminal and this is the third terminal and this is the fourth terminal. Means the resistors are connected different points one after one, okay. Then you can call it as a, these resistors are in a series combination, okay. And in this particular case, you can see there is only one path for the current, okay. If there is a, for example, there is a current, let's consider there is a current. How many paths are there for the current? Only one path. Therefore, current will remain same, okay. Current will remain same, constant, okay. And what happens with the potential difference? Potential difference is given by, okay, potential difference is given by I into R. As it is depends on R, this is the constant, okay, this is constant. Therefore, V is directly proportional to the R. So it depends on R. Therefore, V going to change. V going to change. Means the potential difference is going to change. Getting a point? Now, what about the parallel combination, okay? Parallel combination. Parallel combination. Parallel combination, okay. So what is this parallel combination? So between 2 points, okay, between 2 points, any number of resistors, okay, any number of resistors. For example, here I have considered 3 resistors, okay. Between 2 points, okay, between 2 points, resistors are connected, means one by one, okay. So this is, let me consider 1. This is point A and point B. Let's consider end A and end B. So this is R2 and this is R3. So how many ends are there? Only 2 ends. That is end 1, that is the A end, and this is the end B. Between 2 ends, 2 terminals, all the resistors are connected. So this kind of arrangement we call it as a parallel combination. But whereas the previous one, here you can see how many terminals are there? A, B and C and D, 4 terminals. Or else these resistors are connected one after one, okay. So if the resistors connected at a different points or different terminals, we can call it as a series combination. If all the resistors are connected between 2 terminals or 2 points or 2 ends, we call it as a parallel combination, okay. Now in this particular case, if there is a current, okay, if there is a current flowing through it, as this current has a multiple paths, okay, this is the one path and this is second path and this is the third path. So what happens? The current will divide. Let me consider this is the path 1, I1. Let me consider this is the path 2, this is I2, and this is path 3 and this is I3. After reaching this point, again this is I only, after joining all the current. So in this particular case, as I changes, okay, as I changes, okay, I changes, okay. And what happens to the other quantity? Other quantity remains same, okay, because so between 2 terminals, okay, between two terminals, see the potential difference remains same, okay. Between 2 terminals, potential difference remains same. Between terminals, potential difference same. Getting a point? So don't get confused between 2 terminals. Whatever the current is coming and whatever the current is going. Okay, for example, here 4 ampere, here 4 ampere. Okay. So if 4 ampere is same, means the current is same, therefore potential difference same. But in between, the current is dividing. So therefore, the potential difference across R1, potential difference across R2, potential difference across R3 remains the same. Why? Because this I3 is changing. Means I1, I2, I3. Fine. Now, applying the same rule here. Series circuit. Series circuit means current remains same. A closed circuit in which the same current flows through all the components and voltage in the circuit. Okay, voltage in the circuit is equal to the sum of individual voltage across all the components. That is the resistors. Okay. Okay, resistors. So first let me consider resistors. Okay, so as it is a series combination, let me consider two resistors. Okay, two resistors. Okay, fine. So now yes, so these indicates wires. Fine. And this is the plug key, and this is battery, and this is ammeter. Okay, this is plus and this is a minus. Fine. So this is a plus and this is a minus. Here closed means the current is flowing. So current is flowing in this direction, high potential to low potential, and this is R1 and this is R2. Okay, and this is ammeter, and this is the potential difference. Okay, and current through the resistor 1 and resistor 2, it is the same. Okay, this is I and this is also I and this is also I. Okay, as a single path, the current will remain same. So in this particular situation, okay, so current is same as current is a constant. Okay, current is constant. Okay, and V, what happens to the V? So for example, this is across I1 and this is V1 and this is I2 and this is V2, means current and voltage across resistor 1 and resistor 2. So V, what happens? That is sum of individual voltage across all the components. How many components are there? 2, R1 and R2. So V1 and V2, V1 plus V2. Okay, from Ohm's law. Okay, from Ohm's law, V is equals to IR. Okay, so here what I'll do, so V means I into R series combination. Okay, RS, resistors in series combination, means the resistance of a resistors in a series combination. V1 means I1 R1 and V2 means I2 R2. By this concept, as current is same, therefore I is equals to RS. I1 in place of I1, this is R1 I in place of R1 as it is, and in place of I2, that is also I into R. Okay, on the right hand side you can see I is constant, therefore take it outside. R1 plus R2, and here you can observe I and I get cancelled. So finally resistors in a series combination. Okay, resistance of a resistors in a series combination, that is given by R1 plus R2. So directly you can add. Okay, directly you can add in case of a series combination. In case of a series combination, got it? Now let's move on to some important points regarding resistors in a series. Okay, see, first point. In a series combination, the current has a single path for its flow. Hence, the same current passes through each resistor. So potential difference across any resistor is directly proportional to the resistance. Okay, it's a resistance. Thus, potential difference is different across different resistance. Okay, according to that, V is directly proportional to the resistance. Now, second point, the equivalent resistance is equal to the sum of individual resistances. Here you can see, here we have used only two resistors, therefore R1 plus R2. If I use a few more resistors, for example R3 and R4, the sum R1 plus R2 plus R3 plus R4. Okay, so this RS indicates the total resistance of the circuit or else equivalent resistance of the circuit. All right, okay, so this one indicates, okay, this one indicates total resistance or equivalent resistance or I'll write here, okay, equivalent resistance, total resistance, equivalent resistance, or resultant resistance. Got it? Okay. Now, let's move on to the second important point. Already we discussed about it. Okay. Rs is equals to R1 plus R2 plus R3. Now, third point. In general, if n resistance means n number of resistors, here we have used only 2 resistors, right? So what if I use n resistors? Identical means resistance values are same. Okay, for example, 5 ohm, 5 ohm, 5 ohm, 5 ohm, 5 ohm, and so on. Or else 10 ohm, 10 ohm, 10 ohm, and 10 ohm, so on. Okay, like that. So you can add directly. Okay, you can add directly. If n equal resistance, as I said, it is a 5 ohm, 5 ohm, 5 ohm, or a 10 ohm, 10 ohm, 10 ohm. That is the fourth point. Okay. So in our circuit, let's see. So here circuit is open because there is key. So so first let's consider ammeter means current. We will measure it. Okay. As the key is open, there is no flow of current. So what I'll do, I'll close the key. Now you can see something is moving, right? Something is moving. So left hand side, right hand side to left hand side, anti-clockwise, something is moving. Okay. So here we have resistor 1 and resistor 2. So first we'll calculate resistor current across. Uh, yes, current across. Uh, yes. Hmm, hmm. So what is the current here? That is 0.45 ampere. Okay. If we consider the value of a resistance, okay, that is the 10 ohm, and the value of this resistor, that is the 20 ohm. Okay. So current is current across this resistor, that is the 10 ohm resistor, that is 0.45 ampere. Okay. Now let's see. Across this one. Hmm. So here something is different because here I have used wires, right? So that is the reason it is not visible. Okay. So this is how series combination looks like. Now let's move on to the parallel combination. Okay. So let's move on to the parallel combination. Before that, here we have one question. Okay. Simple question. The question says, an electric lamp whose resistance is the 20 ohm and a conductor of 4 ohm resistance are connected to 6 volt battery. Okay, in this figure. Calculate the first question. A, the total resistance of a circuit. B, the current through the circuit. And C, potential difference across the electric lamp and conductor. Okay, so that means they are talking about this is the conductor, that is the 4 ohm. Okay, this is the 4 ohm, and this is how much it is, electric lamp of a 20 ohm resistance. Okay, and a potential difference of a 6 volt. So first we need to calculate total resistance of the circuit. Total resistance of the circuit. Okay, total resistance of the circuit. Total resistance of the circuit. Okay, total resistance of the circuit. Total resistance of the circuit. So what I'll do are, and what is the combination here? It is the 4 ohm and it is the 20 ohm. It is in a series combination. Okay, what is the combination means? It is a series combination. One after one, the resistors are connected. Therefore, it is a series combination. So Rs, that equals to 4 plus 20, that is 24 ohm. Okay, total resistance of the circuit, that is the 24 ohm. Now, next question, B question. What is that? The current through the circuit. The current through the circuit. The current through the circuit. According to the Ohm's law, V equals to I into R, right? But here we are using total resistance, right? Therefore, RS. So here we need to find out the current. Therefore, rearrange that equation. What we will get? So V divided by RS. Okay. So V, that is the 6 volt, divided by RS, that is the 24. Okay. So 1 divided by 6 ones are, and 6 fours are 24. Okay. So 6 fours are, and this is going to be 0.25 ampere. Okay. So current in the circuit, that is given by 0.25 ampere. Now, next question C. Next question C. Next question C. C question. What is that question? Let's check out. The potential difference across the electric lamp and conductor. So they are talking about a V1, array, V1 and V2. Okay. So V1 across the conductor, V2 across the lamp. Okay. So let's write potential difference across a conductor. Okay, so that is the V1, right? V1. So across V1, what we have to do it? So current I into R1. I into R1. And already we got to know what is R1. That is the resistance of a conductor, that is the 4 ohm. Okay. So V1, that equals to, I is also, we know that is 0.25. Why it is not a I1? Because it is a combination, series combination. Okay. In a series combination, current will remain same. Therefore, 0.25 ampere only. So 0.25 into 4. Okay. So V1 that equals to 0.25 into 4, that is the 1 volt. Okay. Across the conductor. Now, next one, potential difference. Okay. So potential difference. So potential difference across the lamp. What is the resistor? First V2. Okay. What is the resistor of, or else you can say, what is the resistance of a lamp? Resistance of lamp. The electric lamp whose resistance is 20 ohm. Okay. Let me consider that is the, by the data you can write R2, that is the 20 ohm, and the current we found that is 0.25 ampere. Now we need to calculate V2, that is given by I into R2. So V2 that equals to I value, that is 0.25 into 20. Okay. So 0.25 into 20. So finally, you will be having 2.5 into 2, that is a 5. So to eliminate this one, 2.5 into 2. Okay. 2.5 into 2, and 2.5 can be written as 5 by 2. 5 by 2 to get cancelled. So 2.5 double, that is the 5 volt. Okay. So finally, V1 1 volt and V2, that is the 5 volt. Okay. So if we add these two, what should be the value? Source voltage. Okay. So source voltage V1 plus V2. Okay. To cross check. Okay. 1 plus 5, that is V is equals to 6 volt. Okay. So what is the source voltage? Source voltage, that is the 6 volt. Okay. Right. We got the right answer. Now let's move on to the next one's resistors in a parallel. In a resistor in a parallel combination. In a parallel combination, potential difference remains same, but current vary. Right. So current will vary. So parallel circuit. Parallel circuit is the closed circuit in which a potential across all the components is the same, and current is different among the different components, their sum is equal to the total current in the circuit. So what is the circuit of this parallel combination? Let's consider two resistors. Okay, two resistors. Okay, two resistors. Two resistors. So diagram should be very neat. Okay. Yes. Okay. So parallel combination. And here also parallel combination. Okay. So let me consider this is R1 and this is R2. And this is a plug key. This is high potential and this is low potential. And here ammeter. Okay, so this is positive and this is negative. And this positive and negative, and here plug key, and here voltage, and resistor 1 and resistor 2. And current will be flowing. Current will be flowing, and here current will divide I1 and I2. Okay, so after reaching this point, again I will flow. That is the total current. Okay, so this is the circuit diagram. Now, according to the concept, so V constant means the same, and then current changes. Okay, current changes. So total current is divided into two parts, I1 plus I2, and from Ohm's law, V is equals to I into R. So in terms of I, we can write V divided by R. Okay, as it is the parallel combination, can I write it as a V divided by R? Okay, total resistor, that is in terms of a parallel combination, RP. That equals to I1. I1 can be written as V divided by R1 plus V divided by R2. Okay. Why V1? Why not V1 and V2? Because V is a constant. Potential difference is constant. Okay. And V taken out as a constant, 1 divided by R1 plus 1 divided by R2. Okay. So here you can consider V and V get cancelled. So finally 1 divided by RP, that is a parallel combination, or else equivalent resistance of the circuit, or else total resistance of the circuit. Okay. Now, so 1 divided by R1 plus 1 divided by R2. Okay. This one can be rearranged. How? RP is equals to R1 into R2 divided by R1 plus R2 after taking LCM and rearranging the equation. So this is our expression for total resistance or equivalent resistance or resultant resistance of this circuit. Okay. Now, so here V and here also V. Now, important points related to resistors in parallel. The first important point, the potential difference across each resistor is the same, which is equal to the potential difference across the terminals of the battery or a source. Whatever the potential by the source, okay, whatever the voltage provided by the source, that will be the potential difference across each component. Okay. Now, next one, the equivalent resistance Rp is given by 1 by Rp is equals to 1 by R1 plus 1 by R2 plus 1 by R3. Here they have used 3 resistors. Okay, they have used 3 resistors, therefore 1 resistor extra. Okay, now next one. In general, if n resistance joined in a parallel, n resistance, 1 by R1 plus 1 by R2 plus 1 by R3 and so on 1 by Rn. N means n resistors. What if all the resistance value are same? Okay, so for that, here we have a fourth point. If there are n equal resistances, each of value are connected in a parallel, the equivalent resistance is 1 divided by Rp is equals to 1 by R plus 1 by R plus 1 by R and so on n times, that is equals to n divided by R. So if all the resistance values are same, you can do it 1 by R. R means the value of resistance. Okay, value of resistor. Last one, in parallel combination, the equivalent resistance Rp is less than even smallest resistance are connected. What does that mean? For example, 2 resistors. Okay, 3 resistors, let's consider. 1 ohm, R2, that is a 2 ohm. Okay, and R3, let's consider a 3 ohm. Okay, so Rp value will be less than 1 ohm, which is the least resistance, this 1 ohm only. The equivalent resistance will be less than 1 ohm. In case of a series combination, if I consider the same R1, R2 values, okay, if I consider R1, R2 values, here you see R1 is equals to 1 ohm, R2 value equals to 2 ohm, and R3 value equals to 3 ohm. Okay, so RS value always greater than 3 ohm. Okay, always greater than 3 ohm. See that point, fifth point is very important. I forgot to explain this one. Okay, in the series combination, the equivalent resistance RS is more than even the largest resistance is connected. Which is the largest resistance? This one. Okay, which is the largest resistance? 3 ohm, and equivalent resistance is greater than 3 ohm. How, sir? So according to the series combination, what is the total resistance formula? R1 plus R2 plus R3. So if we add all these 3 quantities, okay, R1, R2, R3, 1 ohm, 2 ohm and 3 ohm, 6 ohm. That is 6 ohm is greater than 3 ohm. That's what I'm writing. Okay, in the same way for parallel combination, but it is a very small resistance. So in case of a series combination, the total resistance will be maximum. In case of a parallel combination, the equivalent resistance or total resistance will be least. Okay, so that is the reason we do refer parallel combination in our household circuit. Okay, there are so many reasons. Okay, all the electrical appliance gets a same potential difference, nothing but a voltage, and heat production is very less, and equivalent resistance will be very small in case of a parallel combination. Okay, now let's move on to the next concept. Yeah, question. The question is, in the circuit diagram given in the figure 11.10, this one, okay, resistor R1, R2, R3 have values of 5 ohm, 10 ohm, 30 ohm. Okay, so let me write here. So this is the 10 ohm, and this is the 20 ohm, and this is the 30 ohm. Okay, which have been connected to a battery 12 volt. This is a 12 volt battery. Okay, 12 volt battery. Calculate. Okay, here this is the battery. Okay, 12 volt. First one, the current through each resistor. B, the total current in the circuit. And C, the total circuit resistance, means total resistance of the circuit. Okay, the first one. Okay, first one, let's consider first one. What is that? Current through each resistors. The current through each resistor. Okay, current through each resistor. For example, if I divide this one as I1, and this is I2, and this is I3. Okay, so first let me consider I1. So formula will be, as potential difference is same, therefore it will be V divided by R1. Okay, so substitute in the values, that is the 12 divided by 10. So that is 1.2 ampere. Okay, 1.2 ampere. Next one, I2. Same V divided by R2. Why V? V1, V2. Why don't we use V1 and V2? Because potential difference in case of a parallel combination, that will remain same. Okay. And this is the 12 divided by R2, that is the 3. 30. The resistance is 30, right? 30 or 20? 10. This is the 10, okay? This is a 10. This is R1, 5. The first case is 5, okay? Here I have written wrong. This is a 5, okay? And after simplifying, 5 2s are 10, 5 2s are 10, 5 4s are 20. Okay, 2.4 ampere, and this is 1.2 ampere, okay? This is 1.2 ampere, okay? Now, last one, I3. So that is V divided by R3, that equals to 12 divided by 30. Okay, so that is the 0.4 ampere. Okay, 0.4 ampere. If we add all the, okay, this is what they have asked. The second point, that is total current in the circuit. 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 Okay. So what you have to do? I is equals to I1 plus I2 plus I3. Okay. I equals to, what is the value of I1? 2.4, 1.2. 2.4, 1.2 plus 0.4. Okay. 0.4 ampere. Therefore, current that equals to 4 to 4, that is the 10, 2, 1, 3, 3, 1, 4. 4 ampere. Okay. 4 ampere. 2.4 into 2.4 plus 1.2, 3.6, 3.6.04, 0.04, that is the 4 ampere. And the next one, okay, next one, a C point, okay, C. What they've asked, the total circuit resistance means total resistance. Total resistance, okay. Total resistance, okay. Total resistance, what is the combination? Given combination, that is a parallel combination. Why, sir? Why parallel combination? All the resistors are connected between 2 points, okay? Between 2 points. Therefore, it is a parallel combination, okay? Parallel combination. Parallel combination. What is the formula? Parallel combination. What is the formula? That is total resistance in a parallel combination 1 by R1 plus 1 by R2 plus 1 by R3. Okay, substitute the values. 1 by 5 plus 1 by 10, 1 by 30. Let's cross check. So 5, 10, 30. Yes. 5, 10, 30. Take the LCM. So if we take LCM 30 and this one 6 plus 3 plus 1. So 6 plus 3, 9, 9 plus 1, 10. 10 divided by 30. Okay. And 1 divided by Rp, that equals to 10 by 30. That is nothing but 1 by 3. So Rp value that is equals to 3 ohm. Okay. So 3 ohm. If you want to cross check it, okay. If you want to cross check it, you can check it, okay. Current you can check it, okay. So current is equals to total potential difference divided by total resistance, okay. Total potential difference, that is a 4, total resistance, that is a 3. So I that equals to 12 divided by 3, that is a 4 ampere. Correct. Cross checking. Okay. Now let's move on to the next question. Here the question is simple. In a figure 11.12, R1 10 ohm, R2 40 ohm, R3 30 ohm, R4 20 ohm, R5 60 ohm, and a 12 volt battery is connected to the arrangement. Here the arrangement. Calculate the total resistance in the circuit, and B, the total current flowing in the circuit. Okay. So first you try to concentrate here. Okay. R1 and R2. What is the R1 value they have? R1 value they have given a 10 ohm, and this one R2, that is a 40, right? So this is a 40 ohm. Okay, so let me consider this entire combination as a combination. Okay, so let's find out Ra value. Okay, for a okay, so combination is parallel combination, therefore 1 by Rp, that equals to 1 by R1 plus 1 by R2. Okay, so what are the values? That is the 10 plus 40. Okay, so take the LCM, that is a 40, and this is 4 plus 1. Okay, so 5 divided by 40, so that equals to, so 5 ones are 5 and 5 eights are 40, 1 divided by 8. So that means Rp value, that equals to 8 ohm. Okay, second one, for B, okay, for B here, it is also parallel combination. Okay, it is also parallel combination, you can see. So 1 divided by Rp, that equals to 1 by R3, 1 by R4, 1 by R5. Okay, what is the value of 1 by R3? R3 value, that is the 30, plus R4 20, plus R5 60, 1 by 60. Okay, so take the LCM. If you take the LCM, that is the 60, and this is the 2, and this is the this one R3, that is the 2, and this is the 3, and this is the 1, that is the 6 divided by 60. Okay, so 1 by Rp, that equals to 1 by 10. Okay, 1 by 10 after simplification. Okay, 6 ones are 6 ones are, so that means 1 divided by 10. Okay, so Rp value, that is the 10 ohm. Okay, now after combining A and B, okay, after combining A and B, so this resistor, RA resistor, for example, if I consider this is a if I consider this as a RA and this one as RB, okay, and this RA and RB are connected in a series because there will be only one path for the current. Okay, so now combining for combination A and B. Okay, so that is a series. For a series combination, so series combination RA plus RB. So what are the values? Series combination, that is the 8 ohm plus 10 ohm. So RS, that is equals to 18 ohm. Okay, 18 ohms. Fine. So total resistance of the circuit is done. Second one, total current flowing in the circuit, total current. Okay, so total current, second one, B point, second one, B point, total current. Okay, total current. So total current, that is equals to V is equals to total voltage divided by total resistance. Okay, that is the RS. Fine. So now V value, how much it is? V value, that is the 12 volt. Okay, yes, 12 volt divided by 18. Okay, and here 6 2s are 12 and 6 3s are 18, and here 2 by 3. So 2 by 3, let's calculate. So it is and 2 already 0, 18, and so on. So here you can write this one as 0.67 ampere. Okay, so this is the total current. So only 2 questions. Yes, only 2 questions. Fine. Now let's move on to the next question. Okay, concept. What are the advantages of a parallel combination over series? The first one, advantage, all the electrical appliance in a house, or else you can say it as a household circuits, whatever it is, the TV or fan, refrigerator, whatever it is, all the electrical devices or appliance gets equal amount of potential difference, or else the same potential difference, or else the same voltage. Okay, the first point, each appliance operates independently without being affected by the presence or working of other appliance. Okay, so this is second point I have explained. Okay, second point, it is clear. Each appliance gets you know connected to 220 volt supply for it's a normal working. And the first point you see, for example, let's say it is the combination. Okay, series combination, one after one. So let's say bulb. Okay, this is the bulb, and the next one, fan. So next one, fan. Let's consider a fan. And the next one, which is TV. And this is a series combination. One after one, they have connected. Okay. So there is only one switch, that is a connection, right? Switch, and this is the source. Okay. This is the source, and this is the ammeter. Okay. Right. So if I close it, okay, if I open this circuit, means if I switch off it, okay, I don't want this bulb, okay, I switch it off. What happens? There is a circuit break, means there is no continuous path for the current. Therefore, if I switch off one appliance, fan do not work as well as the TV do not work. Okay, so first point. Second one, I don't want a fan. For example, I don't want fan. I want electric bulb as well as TV to be worked. Okay. So if I switch it off a fan, this bulb as well as the TV do not work because there is only single path for the current to flow, right? So path is breaking. Therefore, there is no current to flow. So that is the reason we do not use, series combination in our home. Okay. And in case of a parallel combination, what happens? Current has a different path, multiple path. Therefore, even if one electrical appliance stop works, other electrical appliance keep on working because it is independent of other electrical appliance. Okay. The last one, heat produced in a parallel combination is less compared to the series. Why? Because when you consider effective resistance or else a total resistance in a series combination, it is more than the largest resistance used in the circuit. Whereas in case of a parallel combination, okay, in case of a parallel combination, the effective resistance of a parallel combination will be least or else less than the least individual resistance used in the circuit. So hence, resistance less means the heat production is also less. If resistance is more means the heat production is also more. You will be having one doubt, sir, on what basis you are saying resistance is directly proportional to the heat production? Yes, exactly. I'm coming to that topic. That is heating effect of a current. Okay, so that is heating effect of a current. Generally, we call it as the heating effect of electric current. Generally, we call it as Joule's law of heating. Okay, Joule's law of heating. Okay, this one is nothing but Joule's law of heating. Okay, so for example, in a current carrying conductor, okay, if it is the current carrying, okay, let's say it is the current carrying for a time t, okay, and this wire has a resistance R, okay, how much heat, okay, how much heat will be produced in this particular conductor? So it depends on three parameters. One is the resistance of the conductor, second one current, amount of current flowing through it, and the last one time for which the current is flowing through it. Okay, got it? Now, so according to that, the first point, okay, the first point, the amount of current passing through the wire means more the current, more is the heat energy. So amount of the current passing through it, okay, I is directly proportional. And the next one, resistance of the wire. So heat, amount of heat produced in the conductor is directly proportional to the resistance of the conductor. Next one, third one, that is the time for which the current is passed in the wire, that is directly proportional. Okay, so combining all together, H directly proportional to the I square R T. Okay, now finally, after eliminating, let's consider proportionality constant as 1. Okay, 1 proportionality constant. So finally, you will be getting I square RT. Okay, I square RT. Okay, right. So heat energy will be calculated in a form of joules only, or else heat, it is also calculated in a calorie also. Okay, but let it be in a joules only. Okay, now let's move on to the next application of heating effect of electric current. Okay, so first one, tungsten. This is works based on effect of heating. Okay, effect of heating. Next one, fuse. Fuse. Okay, fuse, it is made up of lead and tin. Lead and tin. Okay, low melting point. If it is heat is increasing, what happens? This part, okay, this wire going to melt. This wire going to melt. So after melting, there is a breakage of a path for the current, hence there is no current flowing. So hence this fuse safeguarding the electrical appliance. And the last one, this one, water heater, geyser, toaster, all these are, applications of heating effect of electric current. Okay, now let's move on to the last second concept, that is electric power. For example, let's consider AC at our home. Okay, so electric power is nothing but the amount of energy, or else the rate at which electrical appliance consumes energy is called electric power of that electrical appliance. Okay, so the rate at which the electrical appliance consuming electrical energy, so that we call it as the electric power with respect to time. Okay, now by the definition you can see electric power is the rate at which electrical energy is consumed in the electrical circuit. Okay, so formula for this, electric power, it is given by work done divided by time, or power is equals to energy divided by time. Okay, both are correct only. Okay, and what is the SI unit of a power? So directly you can write it is the watt and represented by capital letter W. Okay, so 1 watt, that is equals to, what is the unit of energy? That is 1 joule. Unit of a time, 1 second. So 1 watt is nothing but 1 joule per second. How to define this 1 watt? 1 watt, how to define it? The power is said to be 1 watt when electrical appliance consumes 1 joule of electrical energy in a second. In 1 second. Okay, so this is how you can define it. Now this is a mathematical formula and this is SI unit. Next one, electrical energy. Electrical energy, nothing but the electrical appliance consumes energy, right? So that is electrical energy. Okay, by the definition, generally they don't ask definition, but you need to understand electrical energy consumed by electrical appliance is given by the product of its potential difference and current. Okay, product of potential difference and current, or else there is another way in terms of energy, that is, it is the product of energy as well as the time. Okay, so for a power, okay, electrical energy power, it is given by V into I. Okay, so this is the one way of writing, and power is given by E divided by T. But here I want electrical energy. Just rearrange this equation, P into T. That's what they are saying. Okay, product of power and time. Okay, this is the product of its a power and a time for which it is being used, or else it is used. Formula. So electrical energy is equals to power into time. Fine. Now, what is the SI unit? All the form of energy. Okay, all the form of energy will have a same SI unit, that is a joule. Any form of energy you consider, electrical energy, chemical energy, and kinetic energy, potential energy, whatever the form you consider, SI unit will remain same. Okay, so this is given by joule and represented by capital letter G. Okay, now let's move on to the next concept, that is the commercial unit of electrical energy, and it's very, very important. Okay, generally they'll ask 1 kilowatt. Okay, 1 kilowatt hour. Okay, 1 kilowatt hour. 1 kilowatt hour. Okay, 1 kilowatt hour. To define this 1 kilowatt hour, just remember it is indicating power into time. Okay, power into time. 1 kilowatt hour is the unit of energy, that is the electrical energy. So that is the reason you have a heading commercial unit of electrical energy. Okay, and this is defined by a kilowatt hour is the amount of electrical energy consumed when electrical appliance having a power rating of 1 kilowatts used for 1 hour. Okay, clear? Next one. So before that, here we have one relation. Okay, so 1 kilowatt hour. Okay, 1 kilowatt hour in terms of SI unit. Okay, it is the commercial unit. With respect to SI unit, what is the relation between commercial unit and SI unit? For that, 1 kilowatt. So generally it is nothing but energy in terms of a power into time. Okay, so let's compare them. So energy, that is in terms of 1 kilowatt into hour. So 1 kilowatt into 1 hour. Okay, 1 kilo means it is the 10 power 3 watt. Kilo means 1000 can be written as 10 power 3 watt. And 1 hour, what is the SI unit of a power, right? And what about a hour? Hour is the not SI unit of a time. Let's convert that. Okay, 1 hour is equals to 60 minutes. Okay, and this can be written as 60 into 1 minute, right? And 60 as it is, 1 minute is equals to how many seconds? That is the 60 seconds. 60 seconds. Therefore, 3600 seconds. Okay, 3600 seconds. That is 1 hour is equals to 3600 seconds. Okay, now 3600 seconds. Okay, now this can be written as 10 power 3 into 36 into this 2 can be written as 10 power 2 watt a second. And here 1 watt a second, that is nothing but a joule only. Okay, now so finally this 36 into 10 power 5 joule. Okay, this 1 kilowatt hour. Okay, or this can be written as in scientific method 3.6 into 10 power 6 joule, that is 1 kilowatt hour. Got it? So sometimes in your unit test, your teacher may ask this relation. Okay, that is 1 kilowatt hour is equals to 3.6 3.6 into 10 power 6 joule. Okay, show that. So that kind of questions can be asked now. So how many questions are left? Let's check out. So 1 2 2 questions are left out. Okay, now the question is, an electric bulb is connected to 220 volt generator. The current is 0.50 ampere. What is the power of the bulb? Okay, so here data, first we need to write down data. Okay, data. So first data, then so here potential difference, that is voltage they have given 220 volt generator, and the current they have given, that is 0.50 ampere, and they are asking power of the bulb. Okay, so power of the bulb, and the power of the bulb, we know that in terms of potential difference and current, that is given by V into I. Okay, so power is equals to V, that is the 220 into I, that is 0.50. Okay, 0.50 means half of that. Okay, 110 watt, 110 watt, half of that. Okay, 220 half. Now next question is, and the last question also, an electric refrigerator rated 400 watt operates 8 hours per day. What is the cost of the energy to operate it for 30 days at rupees 3 per kilowatt hour? So commercial unit of electrical energy, what does that mean? Every month we pay electricity bill, right? So that is not in terms of a joule. Electrical energy, it is in terms of a kilowatt hour. So for that unit, we are paying electrical bill. Okay, so we need to calculate how many rupees, or else how much we have to pay for this particular question. Okay, means we need to calculate energy, how many units in terms of a kilowatt. Okay, so kilowatt hour, right? So first electrical energy, so data first. Data is very important. So data, the first data, that is T equals to 400 watt. Okay, but a kilowatt, in terms of a kilowatt we need, therefore what I can write, 400 divided by 1000, if I do it, that will be in terms of a kilowatt. Okay, that in terms of a kilowatt. Is that clear? Now next one, time they have a given how much, 8 hours. Okay, 8 hours per day. What is the cost of energy to operate 30 days? Means into 30 days. Okay, so this is the time, and rupees they have given 3 rupees. First let's calculate energy. Energy is equals to P into time. So substitute the values. So electrical energy and power, that is the 400 divided by 1000 kilowatt into time, that is in terms of 8 into 30 hours. Okay, now so let's see, two zeros get cancelled, 1 0 1 0. Okay, now electrical energy is 4 into 8 into 3 kilowatt hour. Okay, now simple calculations. Okay, simple calculation we can do it here only. Okay, so E is equals to 12 into 8 kilowatt hour. Okay, so 12 into 8, 96. So total how many units you have used in an entire month? 96 kilowatt hour. So this is the unit. And cost for, okay, cost for 96 kilowatt hour, that equals to 1 unit per unit, that is the 3 rupees. Okay, 3 rupees into 96 into 96, 288 rupees, or else you can write rupees 288. Okay, this is how you need to calculate, cost of energy that we used in a month. Okay, right? So that's all, I think. Now let's move on to the homework. What do you need to do after this? So first, revise today's lecture, highlight important concept or questions, and note down your doubts in the notebook if any. And last one, go through PYQs. Okay, go through the PYQs. So without a fail, go through the PYQs at least 5 years. Okay, 5 years PYQs you have to solve it. Okay, based on this particular chapter. Okay, so that's all for today's session. Take care. Bye bye.